Hello there, and welcome to Sleepy Cosmic Podcast, where we wander beneath velvet skies, following ancient light on its unhurried path through time. If this kind of quiet wonder helps you rest, I'd be grateful if you tap like or subscribe, no pressure at all. And if you'd like, you can whisper where you're listening from tonight, and what time it is there. Now, dim the lights, maybe turn on a fan for a soft background hum, and let's ease into tonight's journey together. Above the red horizon of Mars, a small light shimmered where none should be. It wasn't a flare from the rover, nor a trick of dust suspended in the thin Martian air. It was motion, slow, steady, unmistakably celestial. On October the 2nd, 2025, NASA's Perseverance rover tilted its small upward-facing skycam toward the copper sky and captured an image that would ripple through the quiet corridors of science, a speck of brightness, circled in green by NASA's own hand, traced across the Martian morning. It was designated 3I Atlas, the third confirmed interstellar object ever seen, and the first to be photographed from another world. That's a strange milestone when you think about it. Across billions of kilometers, between two small planets orbiting an ordinary star, a camera built to watch dust storms and clouds had caught a visitor older than our entire solar system. We had seen interstellar wanderers before, Oumuamua in 2017, Borisov in 2019, but always from afar, always in retreat as they slipped past Earth and away into the black. This time, though, Mars happened to be in the right place. The rover's camera, designed to look up through a pink-gold haze, found itself facing an object that had come from somewhere beyond the sun's reach, moving through the light like a thought crossing a dream. The image itself wasn't dramatic. No tail streaked behind it, no grand plume of fire. Just a white dash against the sky, small and faint, its presence verified only by motion between frames. Yet in that minimal movement lay everything: velocity, distance, proof of reality. For scientists, even a single pixel can whisper truth if you listen long enough. On Mars, the morning was cold. The sky there is never truly blue. Dust scatters sunlight into shades of butterscotch and rose. When the camera recorded its frames, the sun was already 3 hours high, and the shadows of Perseverance's instruments stretched across the deck like clock hands. To capture something as dim as 3I Atlas in that brightness meant the object was glowing with unusual strength, its surface or its coma reflecting sunlight across 30 million kilometers of emptiness. For a few brief seconds, that light fell through alien air and onto a human machine, a message written in photons older than the camera's creation. You can imagine the engineers back on Earth, still half asleep in Pasadena or Madrid or Canberra, watching the data trickle home through the deep space network. Most days, it's routine. Images of rock layers, dust devils, the endless sameness of Martian geology. But that morning, the feed contained something different. A glint in the sky, a line of pixels that didn't belong, and then the realization. The rover had captured an interstellar object from the surface of another planet. Think of what that means in cosmic terms. Our tiny species, still learning to keep machines alive across space, had accidentally turned one of them into an interstellar observatory. Not from orbit, but from the dusty skin of a world that's been silent for billions of years. That small upward camera, built mainly to check for dust, had become a window between stars. The science team verified the coordinates. The motion was consistent with the known trajectory of 3I Atlas, a body moving roughly 67 kilometers per second relative to the Sun. Fast enough to cross the distance between Earth and Mars in under a month. Fast enough to escape any gravitational bond our system could offer. At that speed, a grain of sand carries the energy of a bullet. An iceberg of rock and metal carries the quiet momentum of eternity. No one expected Perseverance to capture such a thing. Its optics weren't designed for astronomy. The Martian atmosphere, though thin, scatters sunlight into a bright haze that drowns faint stars. Yet against those odds, the object appeared. It's almost poetic how the first interstellar object ever seen from another planet wasn't caught by a telescope, but by a weather camera glancing absently at the morning sky. Maybe that's how discovery often happens, not in grand design, but in still moments when a machine, or a person, simply looks up. After that first photo, scientists traced the object's predicted path. In just 24 hours, it would reach its closest approach to Mars, a rare alignment of geometry and luck. 7 spacecraft, orbiting or resting on the red planet, would have a chance to watch it. Their instruments could measure brightness, velocity, perhaps even the composition of its coma, the cloud of gas and dust that forms as sunlight warms the surface. The last time humanity had this kind of opportunity was never, not in any recorded observation. This was the first time in all of human history that multiple spacecraft stationed beyond Earth could examine a body from another star at close range. For those of us who love astronomy, that's the quiet kind of miracle that happens without applause. No bright headlines, no live broadcast, just a few teams across the world turning their instruments toward an object crossing another world's sky. It's the purest form of curiosity, no agenda, just the hope that the data might whisper something about where we came from, or where we might someday go. In the raw images, the object appears elongated, perhaps a motion blur from the long exposure, perhaps something real about its shape. Later analyses suggested it was roughly 4 times longer than it was wide, with faint hints of green along its edges. Some said the green was a camera artifact, a byproduct of stacking exposures. Others wondered if it was an actual colour, a clue to metallic composition or unusual chemistry. The truth, as with so much in science, remains soft around the edges. Certainty is a rare luxury when you're staring at a light that left its source years or millennia ago. Still, the image existed. An interstellar visitor seen from Mars shining in thin sunlight, framed by a sky the colour of faded rose. It was a moment of connection across time and distance, a reminder that exploration isn't only about reaching farther, but about noticing what drifts quietly past. Perhaps one day, when humans stand on that planet themselves, they'll look up and remember this first photograph, the way a small robotic observer lifted its gaze to the sky and caught a ghost from another star. In that image, the red world and our blue one share something. A glimpse into the endless migration of objects through this galaxy, and the realization that even across 30 million kilometers, a spark of curiosity can bridge the void. When the faint light above Mars was confirmed, a quiet choreography unfolded across the solar system. 7 spacecraft, some orbiting, some roving, all designed for other purposes, turned their attention toward a single moving speck. For a brief moment, 4 nations shared the same cosmic goal: to capture an interstellar traveller as it passed through the gravity well of a neighbouring world. It was one of those rare alignments of both orbit and intention, where mathematics and curiosity overlap perfectly. Each spacecraft had a different vantage point. NASA's Mars Reconnaissance Orbiter circled high above, its camera capable of astonishing precision, while ESA's ExoMars and Mars Express prepared their own imaging sequences. China's Tianwen-1 waited in another orbit, its sensors ready to detect faint signatures, and the UAE's HOPE mission, built to study Martian weather, adjusted to capture the visitor's spectral profile. Below them all, Perseverance and its older cousin Curiosity stood still against the ochre sand, their upward lenses like open eyes. Together they formed a web of instruments more far-reaching than any telescope network on Earth. It's rare for such coordination to occur outside of planned experiments. Spacecraft operate on careful schedules, governed by power constraints and communication windows. Every image, every data packet has to compete with mission priorities. But sometimes, the universe itself offers a reason to pause. This was one of those times. Scientists on Earth called it a cross-agency alignment. A moment when independent programs, each with their own languages, funding and politics, found themselves facing the same patch of space. The odds of that are small enough to feel almost poetic. To think that while Mars spun silently below, 7 machines, separated by millions of kilometres and decades of engineering heritage, were all focused on the same unknown. From Earth, telescopes joined in. The James Webb Space Telescope aimed briefly toward the object during a calibration window, while smaller observatories across Chile, Hawaii and the Canary Islands tracked its trajectory through the black. For a few days, humanity's attention stretched across both worlds. If you could look at it from far above the solar system, it would appear like a momentary glint, a handful of artificial satellites clustered around Mars, all turning their sensors toward a single spark approaching from interstellar space. At its core, this coordination was a kind of instinct. For all our technology, astronomy remains an act of reverence. We point our instruments at the unknown not because we expect to own it, but because looking is the only way to understand. And 3i Atlas, drifting between planets, offered the purest possible reason to look. It wasn't large by cosmic standards, perhaps a few kilometres across, but scale loses meaning in space. What matters is context. Here was a body older than our sun, passing close enough to study in real time. For astronomers, it was like a fossil tumbling into view from a long-buried epoch. Every particle of its dust carried stories from another star system, its chemistry shaped by conditions utterly foreign to ours. The spacecraft aligned their instruments. Some tracked visible light, others infrared, others ultraviolet or gamma rays. Each wavelength reveals a different layer of truth. Visible light tells us about reflection and colour. Infrared reveals heat, texture and composition. Ultraviolet traces energetic outgassing, those faint plumes of vapour escaping into space. Together, they would form a mosaic of data that could describe not just what the object looked like, but what it was made of and how it behaved under the sun's warming gaze. There's a quiet beauty to this process. Long before the data reaches Earth, before scientists debate or publish, there's that silent moment when photons, after travelling for years through space, strike a sensor and become numbers. Light transformed into code. That code becomes thought, and thought becomes understanding. But understanding takes time, and time in deep space moves differently. Communication between Mars and Earth carries a delay of anywhere from 4 to 20 minutes, depending on the planet's positions. That delay, multiplied across thousands of image sequences and telemetry packets, creates a kind of breathing rhythm, a slow conversation between worlds. When those 7 spacecraft began collecting data, no one expected immediate answers. The light they captured would have to be compressed, transmitted, decompressed, decoded, calibrated, and analysed. That process can take days, even under normal circumstances. Still, there was something eerie about what happened next. After the observation windows closed, data stopped flowing. No images were released, no press statements, not even the usual hints that preliminary analysis was underway. For days, the silence deepened. On social media, astronomers shared guesses. Was it just the complexity of data transfer, or had something gone wrong with one of the missions? Others, more imaginative, wondered whether the agencies had agreed to withhold results until everyone compared notes. That kind of cooperation does happen occasionally, but not across nations that usually compete for first release. The stillness became its own kind of signal. Somewhere in that stillness, a sense of awe mixed with unease. When telescopes on Earth observe a new comet, images appear within hours. When spacecraft pass an asteroid, the first pictures are shared almost instantly. But this was different. The quiet coordination that had united 4 agencies seemed to dissolve into collective reticence. Perhaps they were cautious. Perhaps the data didn't make sense yet. Or perhaps they saw something no one could explain in a single headline. In the vastness of space, even silence has meaning. When every instrument in orbit looks at the same thing and then falls quiet, it's as if the universe itself has whispered a secret too heavy to repeat right away. For the scientists involved, the waiting began. And for those of us back on Earth, staring up at skies we can't see from Mars, that waiting turned into wonder. The object would continue its path, drawing closer to the sun, fading into glare, and leaving us with one unanswered question suspended between planets. What did they see when they looked together? For 4 days there was nothing. No press conferences, no images, no reassuring statements about calibration delays or bandwidth issues. Just silence. An unusual, deliberate kind of silence that wrapped itself around the astronomy community like fog. It began as quiet patience. Scientists are used to waiting. Spacecraft transmit through narrow communication windows, and the data must pass through the deep space network. 3 great dishes in California, Spain, and Australia that share the sky like a rotating heartbeat. Sometimes packets take days to clear, but this felt different. Something had paused the rhythm. The first day, observers shrugged it off. The second day, they began to whisper. By the third, every major astronomy forum was alive with speculation. People checked the raw image archives for Perseverance, for Mars Reconnaissance Orbiter, for Tianwen-1, and found nothing new. No updates, no signal that the images even existed. Then the 4th day came, and finally, a voice broke the stillness. It wasn't NASA or China or the UAE, it was the European Space Agency. A short press release, understated and calm, announcing that images of 3I Atlas had been captured by ExoMars and Mars Express. No fanfare, no colour correction or cinematic detail, just a confirmation. Yes, the object was there. Yes, it appeared comet-like, and yes, the data were being studied. But the images themselves told another story. They showed a fuzzy white speck, barely distinguishable from background stars drifting slowly through the frame. It was unremarkable in appearance and yet somehow profoundly unsettling. Because if the object looked ordinary, if it looked like every other comet humanity had seen, then why had everyone else stayed silent? The ESA release didn't answer that. It didn't even acknowledge the absence of data from the other agencies. The tone was careful, measured, a little too polished, almost as if the words had been chosen not only to inform, but to reassure. In one paragraph, ESA scientists mentioned that the images were taken from roughly 30 million kilometers away, far beyond the instrument's intended design range. The brightness was so faint that 5-second exposures were needed, longer than usual for orbiters optimized to image a bright Martian surface. They cautioned that the object's nucleus couldn't be resolved, that we were seeing only the surrounding coma, a haze of gas and dust formed as sunlight vaporized surface ice. A normal phenomenon, they said, entirely consistent with standard comet behavior. And yet, those words echoed oddly against the silence elsewhere. If this was truly so normal, why had NASA not released its images? Why had China, which publishes thousands of Mars photos a year, said nothing? Why was the UAE, usually eager to share data, also quiet? Sometimes the absence of noise carries more weight than sound itself. It wasn't only the public who felt this way. Researchers at universities across Europe and the United States began parsing ESA's phrasing line by line, the way cryptographers might examine a code. They noticed the missing details, the lack of chemical composition, the omission of certain instruments, and above all, one curious sentence: further analysis will take weeks or months. Weeks or months. That's a long time to analyze a dot of light. Within that gap, imagination bloomed. Some argued the agencies had seen nothing unusual and simply wanted to avoid overhyping the story. Others suspected something deeper, that 3I Atlas had displayed properties so unexpected that governments preferred to synchronize their messaging. After all, even scientists serve nations. and nations sometimes fear being first to admit the extraordinary. What makes the silence haunting is not what it hides, but what it allows to echo. During those days, millions of people stared at the same low-resolution ESA image, the fuzzy white speck against black, and felt a mix of awe and doubt. You could project anything onto that speck: a comet, a fragment, a machine. It became a mirror for every human hope and fear about what drifts between stars. There's something ancient about that impulse. Long before telescopes, our ancestors stared at the same night sky, wondering which lights were wandering and which were fixed. Every comet that appeared unexpectedly was read as an omen, a messenger, a disruption in the cosmic order. Perhaps that feeling never fully left us. Even now, surrounded by data and equations, we still look for meaning in the flicker of distant light. ESA's cautious announcement did confirm one thing. 3i Atlas was active. It was outgassing, releasing material as it neared the sun. The coma stretched a few thousand kilometers across, proof that heat was awakening ancient volatiles within the object's crust. To planetary scientists, that meant the body was behaving as a comet should. Yet some couldn't ignore how faint it remained, even under solar exposure. It was bright enough to be seen by Perseverance's sky cam under daylight, and yet strangely dim when viewed through powerful orbiters. The paradox made people uneasy. The release also included a small animation, an image sequence stitched into motion. There, in grainy monochrome, 3i Atlas drifted downward against the background stars. Slow, deliberate, silent. It wasn't much, but it was movement. And movement means reality. It was enough to quiet the loudest doubts that the object might have been misidentified. Still, even as ESA shared this meagre glimpse, one question lingered like a shadow. If their data were so limited, what did the others have? NASA's Mars Reconnaissance Orbiter carries the HiRISE camera, capable of resolving objects on the surface of Mars just 30 centimeters wide. Even at 30 million kilometers, its sensitivity should have exceeded ESA's instruments by orders of magnitude. China's Tianwen-1 has its own high-resolution cameras built to rival HiRISE, and the UAE's HOPE mission includes a spectrometer designed to detect atmospheric composition down to minute variations. If those instruments had captured 3i Atlas at close range, they would have seen details ESA could never reach. The shape of the coma, the colour gradients, maybe even hints of metallic reflection or jet structure. And yet, nothing. No statement. No leak. Just ESA's gentle voice filling the void. Perhaps it's comforting to imagine that the silence means nothing. That we simply live in an age where caution outweighs curiosity. But deep down, many astronomers sensed a pattern. This was the same kind of quiet that follows discovery. The kind that precedes a re-evaluation of what we thought we knew. When the first exoplanet was detected in the 1990s, the data sat unannounced for months, while teams confirmed and reconfirmed the signal. When gravitational waves were first recorded, it took years before the announcement. Science often moves at the pace of certainty, and certainty, especially when confronted with something that challenges it, takes time to build. So, for 4 days in October, the universe held its breath. Mars turned under its thin sky. Earth rotated through its blue haze, and between them, light from a visitor beyond the stars continued its path toward the sun, unaware that it had become the subject of quiet human fascination. The stillness that followed the flyby became a kind of mirror for our species. It reminded us how much of discovery happens not in noise but in waiting, in the long silence after first contact, before understanding arrives. When the silence finally cracked, it was the European Space Agency that spoke first. Their words arrived without drama, no cinematic music, no triumphant tone, just a measured announcement. The ExoMars Trace Gas Orbiter and Mars Express have detected the interstellar object designated 3I Atlas. It was calm, almost subdued, the way scientists speak when they're still uncertain what they're looking at. The first image appeared on ESA's website, a faint white blur against a field of dim stars. It drifted pixel by pixel across a stitched animation made from exposures taken between October 1st and 7th. It was small, almost lost in the static, yet there it was. The third interstellar object ever confirmed by humanity, passing near another planet in real time. For all our technology, the image resembled those from a century ago, a ghostly smudge of light, delicate, imperfect, surrounded by darkness. The Cassis camera that captured it was never meant for this. Its full name, the Colour and Stereo Surface Imaging System, suggests its true purpose, photographing the Martian landscape in colour and depth. Cassis was built to map ridges, dunes and cliffs, not to chase comets through interplanetary space. Yet here it was, straining beyond its design, gathering photons from something 30 million kilometres away. That's 100 times farther than its intended focus range, so faint that the team had to extend each exposure to 5 full seconds, an eternity for a spacecraft camera orbiting a bright world. To appreciate what that means, imagine trying to photograph a phone screen glowing on the moon's surface from Earth. That's roughly the level of difficulty, and still Cassis succeeded. The image was fuzzy, yes, but it existed. It told us that 3I Atlas was real, visible, and active. In science, even a faint whisper of data can sing volumes if you know how to listen. ESA confirmed that what we were seeing wasn't the object's nucleus, but its coma, the thin, glowing envelope of gas and dust released as the sun's heat touched its surface. That coma stretched thousands of kilometres, meaning the interstellar visitor was already awake, exhaling material into the void. This, at least, was normal. Comets do this as they near the sun. They become fountains of vapour, their frozen interiors releasing whispers of ancient ice into light. But beyond that, the announcement grew vague. There was no mention of unusual colours or bright jets, no clear statement about its chemistry or temperature. ESA's words remained careful, distant. They said the comet was behaving as expected, yet the tone carried a quiet tension, as if expected didn't fully match what they'd observed. The team acknowledged that other spacecraft, Mars Express for example, had also attempted to image 3I Atlas, but that those results were still being processed. They noted how hard it was to detect something so faint when Mars itself blazed below, its reflected sunlight flooding every sensor. That explanation sounded reasonable, and yet, in the background, one could sense unease, because no one could quite explain why only ESA had chosen to publish anything at all. As the press release circulated, people studied every word, every phrasing. There was one line that caught everyone's eye. Colin Wilson, the project scientist, said, "It's always extra exciting to see orbiters responding to unexpected situations." Unexpected situations. It was an innocent phrase, likely meant to highlight the challenge of the observation, but to those listening closely it carried weight. What exactly had been unexpected? The timing, the brightness, the direction of motion. No one knew, and ESA wasn't elaborating. To understand why, it helps to remember how scientific language works. When researchers encounter something they can't yet explain, they often hide it inside neutral phrases. Unusual data, unexpected variance, requires further analysis. These are the verbal shelters where uncertainty rests until it becomes understanding. So when ESA used that wording, it didn't necessarily mean alarm. It meant they were cautious, maybe even protective, of an unfolding mystery. Behind the scenes, the Cassis and Mars Express teams began stacking images, layering exposures to enhance faint features. This is a common practice in astronomy. By combining multiple frames, the signal of a distant object grows stronger while background noise fades. It's how we reveal what's too dim for any single photograph. The process can take days, even weeks, depending on calibration and alignment. So while the public saw only a blur, the researchers were already deep in the quiet work of refinement. But outside ESA's walls, the absence of parallel announcements grew louder. NASA's website remained still. China's Tianwen-1 mission, normally prolific in sharing Martian photos, released nothing. The UAE's Hope orbiter, which has an entire open-access data portal, stayed dark. The contrast was stark. One agency sharing cautious images, 3 others withholding everything. To some, this was evidence of coordination. Perhaps they suggested the agencies had agreed to synchronize releases once everyone's data was verified. But to others it looked like fear. Fear of publishing something that couldn't easily be explained. The ESA images showed no obvious anomalies, and yet they left behind a hollow sense that something had been omitted. The absence of colour data, for instance, was curious. Cassis can record in colour, but the images shared were grayscale. No temperature readings, no spectral lines, no chemical analysis. Only brightness and motion. Even the brightness scale was left uncalibrated, which meant scientists outside ESA couldn't verify how luminous 3i Atlas truly was. Still, those few frames were enough to ignite debate. Was it truly cometary? Was the coma uniform or asymmetric? Some independent analysts claimed the light distribution seemed lopsided, denser toward the leading edge, a hint of a forward jet perhaps. Others dismissed that as an illusion caused by image stacking. No one could be certain without the raw data, and that data remained locked within agency servers. ESA promised more information in the coming months, which in scientific terms might mean anything from December to next year. They reassured the public that the object was being closely monitored, but their reassurance didn't quiet the curiosity. Instead, it amplified it. When people are shown a mystery and told to wait, imagination fills the silence. And so, around the world, forums and late-night podcasts speculated about what had been seen. Was it just a dim comet after all? Or was the faintness itself unusual, a sign of strange composition, or even of deliberate dimming? No one could say. All we had were ESA's careful sentences, a handful of blurred frames, and that single phrase, unexpected situations, drifting like an echo through every conversation. In the grand tradition of astronomy, discovery often begins this way, not with certainty but with restraint. The sky offers a glimpse, and scientists respond not with exclamation, but with patience, because the first look at a mystery is rarely the moment it reveals its truth. It's simply the first invitation to keep watching, and so on October 7th the silence broke, but only a little. The faint white dot glided through the darkness of the Cassis animation, leaving humanity with a paradox. We had seen it. We had proof it existed. And yet somehow it felt like we still hadn't seen it at all. The faint coma seen by ESA told a simple story, at least on the surface. 3i Atlas was breathing, not with lungs, but with sunlight. The warmth of our star, gentle by cosmic standards, was enough to stir the frozen materials trapped inside the visitor's crust, releasing them in streams so fine that only instruments could tell. To most astronomers, this was comfortingly familiar. Comets do this when they wake. They exhale gas, dust, and vapour that form a fragile veil around their bodies, a luminous sphere called the coma. ESA's statement confirmed that much. It described the coma as several thousand kilometres across, modest compared to giants like Hale-Bopp or Enki, yet large enough to suggest active outgassing. That word is active, carries quiet poetry. It means that somewhere on that distant nucleus, the sun's light had touched an ancient surface, triggering a chain of warmth, evaporation, and motion. We often forget how alive physics can be when it unfolds slowly. A frozen molecule, asleep for eons between stars, suddenly liberated into the sunlight of another system. That's its own kind of rebirth. Still, there were hints that this coma wasn't entirely ordinary. Its brightness profile was strange, evenly distributed rather than sharply peaked around a core. That could mean the nucleus was unusually dark, coated in carbon-rich material that swallowed light. Or it could mean the coma was dense enough to obscure the core completely. Astronomers debate such subtleties because they tell us about history. Every comet's composition is a memory of the environment it formed in. If the coma of 3I Atlas held more carbon dioxide than water, as later reports would suggest, it might have originated near a colder, older star, one with chemistry different from our Sun's. The science is delicate here. Cometary outgassing depends on more than just heat. It depends on which molecules are buried near the surface. Water ice sublimates at higher temperatures than carbon dioxide. So, a comet dominated by CO2 will wake up farther from the sun, glowing before typical comets even stir. And that was exactly what astronomers had noticed earlier that year. 3I Atlas had begun brightening unusually early, at distances where sunlight should barely have warmed it. The team at ESA mentioned none of this directly in their release. Instead, they described the coma as consistent with activity expected from volatile sublimation, a tidy, neutral phrase. But between the lines, experts could read the tension. If the activity matched no known thermal model, perhaps the chemistry was different. Perhaps the comet's interior was rich in materials rare to our system. There's a soft wonder in imagining what those materials might be. In our own backyard, comets are relics of the solar nebula, the dusty gaseous swirl from which the planets condensed 4.6 billion years ago. Their ices are the archives of that era, still preserving traces of primordial water, carbon compounds and organic molecules. But 3I Atlas didn't come from here. It was born in another nursery around another star. Its ices froze under a different spectrum of starlight, its elements forged in different supernovae. When sunlight touched it, the molecules that escaped were not only ancient, they were alien. To see that coma at all was to glimpse the chemistry of another world's dawn. Somewhere in that vapour, there might have been molecules we've never catalogued, perhaps compounds stable only under conditions long vanished from our galaxy. Or maybe the differences were subtle, ratios of carbon to oxygen, hydrogen to nitrogen, that tell quiet stories about cosmic ancestry. Spectroscopy could reveal those clues. But at this stage, ESA said nothing about spectra, only brightness and motion. Their scientists surely were already dissecting the data line by line, but the rest of us had to wait. You might picture it. A handful of researchers huddled over screens at the European Space Operations Centre, their faces lit by graphs and faint traces of spectral lines. Outside, night has fallen over Darmstadt or Madrid or Paris. Inside, they whisper about intensity ratios, calibration drift, and the strange balance of gases in a signal that shouldn't even exist yet. No one speaks the larger thought aloud, that they might be seeing the breath of another solar system crossing ours. For those working in planetary science, this is sacred work. You spend years chasing numbers, orbital parameters, brightness curves, photometric corrections, and then one day, the data before you isn't from your system anymore, it's from the space between stars, and suddenly all the equations feel smaller. ESA's early report focused on the challenge of distance, perhaps to set expectations low. At 30 million kilometres, even the best instruments could only catch whispers. But whispers are enough. Astronomers have always listened to whispers. Radio hums, cosmic microwave background ripples, the quiet glow of dust. Every whisper adds to the conversation between humankind and the universe. The faint coma of the 3I Atlas was one more sentence in that dialogue. It spoke of warmth and release, of motion and memory. It proved the object was not a cold rock tumbling through space, but a dynamic, reactive body responding to sunlight. That meant it carried volatiles, gases that could evaporate under mild heat, and that its surface was being reshaped by that release. In simple terms, it was alive to its environment. In the days after ESA's release, amateur astronomers tried to observe it from Earth. Few succeeded. The object was far too dim, lost against the glare of the sun. Yet that didn't stop the flow of speculation. Some claimed the coma's symmetry was too perfect, suggesting controlled venting. Others argued it was pure coincidence, shaped by solar wind and geometry. Science thrives in that tension between imagination and rigour. To some, those blurred images were proof of engineering. To others, they were simply the limits of optics. And still the coma lingered, faint, steady, unchanging. The dust it released would continue to trail behind, forming a narrow path that telescopes could follow. Each particle, a breadcrumb through space, tracing the course of an object that had crossed light years to pass briefly by our neighbourhood. There's something gentle in that image, a comet leaving its faint trace like a sigh across the dark. We might never know whether its chemistry held secrets beyond our understanding, but even the act of looking reminded us of the quiet vitality of the cosmos. A frozen fragment, warmed by sunlight older than its own star, awakening as it drifted past another world. It didn't need to be extraordinary to be meaningful. Sometimes the simplest confirmation that something so far away can still answer the touch of light is enough to make the universe feel intimate again. ESA's careful report ended with one quiet omission. They confirmed brightness, position, and motion, but the most revealing data, its chemical spectrum, remained uncertain. That single word, uncertain, changed everything. In astronomy, spectra are the fingerprints of matter. Every atom and molecule absorbs and emits light at specific wavelengths. Those patterns form coloured bands that tell scientists what a distant object is made of, what temperature it has, even how fast it's moving. It's the closest thing to touch we have across space. To say a spectrum is uncertain means we haven't yet touched the truth of what we're looking at. ESA's statement explained the problem gently. The object was faint, they said. Its coma might not have been bright enough for spectral characterization. 3 instruments, Omega, SPI-CAM, and Nomad, had been aimed at 3i Atlas, but it was still unclear if they had collected usable data. The sentence was short, but in the measured world of scientific language, it rang loud. If those instruments succeeded, they would know what gases surrounded the object: carbon dioxide, water vapour, methane, perhaps metals. If they failed, then 3 Atlas remained a shape without substance, a mystery defined only by reflection. And yet, the wording felt deliberate. Uncertain is different from failed. It left room for silence, a space in which results could exist but not yet be shared. Somewhere in ESA's data archives, lines of light were being studied, pixel by pixel, for what they might reveal. Spectra carry the kind of intimacy that makes astronomers cautious. They can overturn entire models of formation with a single curve. The discovery that comets contained complex organic molecules once changed our understanding of how life's ingredients may have reached Earth. Finding the wrong ratio of elements in an interstellar visitor could mean something far larger. That the chemistry of other star systems is not just different, but impossible by our standards. That's why the missing spectra mattered. If the data had shown nothing unusual, ESA could have said so. If it had been normal cometary material, water, carbon dioxide, silicates, they would have stated it plainly. Instead, they said the results were uncertain. That single word whispered of complexity, of a signal not yet fitting any expected template. Back on Earth, teams of independent astronomers waited for public access to the raw data. They compared the ESA images with known comet models, trying to predict what the spectra should look like. In simulations, a typical coma near 30 million kilometers would have produced clear peaks of water vapour and carbon dioxide, maybe traces of ammonia. But the brightness ratio suggested something else. Too much reflection in the green spectrum, not enough in the red. That imbalance could mean metallic dust, or it could mean instrument noise. No one could be sure. Perhaps that's why ESA's scientists chose caution. When you stand at the edge of the knowledge, it's easy to mistake noise for novelty. But what if it wasn't noise? What if, buried inside that faint signal, lay an element no one expected to find drifting through another solar system? The mention of uncertainty also deepened another question. Why were the other space agencies silent? NASA's Mars orbiters carried far more sensitive spectrometers, CRISM and THEMIS, capable of detecting even faint spectral lines from millions of kilometers away. If ESA's instruments struggled, NASA's should have succeeded easily, and yet nothing. Not even an acknowledgement that spectra had been attempted. The same was true for China's Tianwen-1. Its Mars orbiter spectrometer for mineralogy could have resolved the coma's chemical structure with far greater clarity. But China too said nothing. That collective quiet began to sound coordinated. It's not that space agencies never delay data. Sometimes they do, for verification or calibration, but they rarely delay together. They rarely fall silent at the same time, over the same object. So the world waited. The astronomy community, the public, even those who don't usually follow space news, all waited for the next announcement. It never came. Weeks passed. The ESA data, still limited, became the only official record of the Mars flyby. Its faint images and uncertain spectra turned into placeholders for understanding. And the longer the silence stretched, the more people began to wonder if those spectral lines, still unshared, contained something disruptive. In quieter circles, scientists debated what that might mean. If 3I Atlas emitted unexpected metals, like pure nickel or chromium without iron, that would challenge every natural model of comet formation. If it lacked hydrogen signatures, it might be more asteroid-like, dense, metallic, forged in conditions unknown. And if its light carried structured patterns, periodic modulations, rhythmic pulses, that might imply something even stranger. But those were only ifs. Science doesn't live in ifs, it lives in data. And the data, for now, remained locked. There's a subtle ache that comes with such waiting. Astronomy is built on patience. Stars evolve over billions of years after all, but humans still crave immediacy. We long for the comfort of closure. Instead, 3I Atlas offered ambiguity. It became a symbol of our limits. We could see it, but not yet know it. The phrase, uncertain spectra, began circulating through scientific journals and online discussions. It became almost poetic. 2 words encapsulating the distance between curiosity and comprehension. It reminded us that the cosmos doesn't yield its secrets on demand. Sometimes, it only gives you a partial reflection, enough to keep you awake at night, wondering what lies hidden in the next line of data. Maybe that's part of the beauty. The unknown isn't a failure of knowledge. It's the landscape where knowledge grows. And so the astronomers kept studying, even as the world outside moved on to other news. Somewhere, deep in the servers of ESA's mission centres, light from another star system was still being decoded. Slowly, cautiously, one uncertain wavelength at a time. In those quiet labs, you can imagine a scientist leaning close to a monitor, tracing a faint curve that dips where it shouldn't. Perhaps the signal is nothing, a glitch, a calibration error, a ghost of scattered sunlight. Or perhaps it's something extraordinary, a spectral echo from an element forged in a sun we've never seen. They won't know until every test is done, every check repeated, every doubt erased. Till then, we wait too. And as we wait, the word uncertain lingers in the air, soft and weightless, like dust illuminated by the first light of morning. reminding us that mystery, not certainty, is what keeps the universe alive. Even as ESA's data trickled out, another puzzle began to form, not in what was said, but in what wasn't. For decades, the cooperation between major space agencies had followed a quiet rhythm. When one made a discovery, the others shared verification. Mars especially had been a stage for collaboration, not secrecy. Images from orbiters and rovers were often released within days, cross-linked between databases, credited across nations. But this time, the rhythm stopped. NASA, China's CNSA, and the UAE Space Agency all held their silence. It wasn't the kind of absence born of bureaucracy. No technical delays, no data under review notices. Just an absence so total it felt coordinated. ESA's release even seemed to hint at it, in an almost diplomatic way. The cooperation between agencies remained strong, they wrote. A reassurance that no one had asked for, unless something behind the scenes had begun to fracture. To the public, this sounded like a line meant to preempt questions. To scientists, it was a quiet red flag. When multiple agencies go dark at the same time, it usually means one of two things. Either the data are incomplete, or they are too complex to explain quickly. In rare cases, it means something entirely unexpected was seen, something requiring joint review before public release. The timing deepened the mystery. NASA was operating under a partial government shutdown that October, limiting communications but not halting them completely. Routine updates about Perseverance and the orbiters continued for other missions. Only the 3i Atlas data stream had gone silent. It was as though one topic had been quietly redacted from the conversation. From a certain angle, that silence seemed almost comforting. Scientists being cautious, refusing to rush interpretation. But from another, it hinted at an unspoken consensus. If all the agencies chose to wait, it meant they were all seeing something worth confirming carefully. The odds of that happening by chance were slim. Imagine it. 7 spacecraft, each run by independent nations, all observing the same object at the same time. If any one of them had captured purely routine data, we'd have seen it. Someone would have released a standard image, a brightness chart, an orbital plot. Instead, nothing. Not even a single frame. ESA's phrasing, unexpected situation, took on new resonance. What kind of situation could unite so many agencies in restraint? To be sure, not everything in astronomy is political. Sometimes it's just the slow heartbeat of verification, scientists ensuring that artifacts and sensor errors aren't mistaken for anomalies. But this felt deeper, older, like the silence before a collective breath. There's precedent for this kind of pause. When Voyager 1 first encountered a strange signal in the 1980s, a narrowband radio spike from beyond Saturn, NASA took weeks to confirm it wasn't from Earth. When the Hubble Deep Field revealed galaxies at unimaginable distances, the images were reviewed by multiple teams before public release. Caution is the mother tongue of discovery. And yet, 3i Atlas carried a different weight. This wasn't just a new comet or asteroid, it was an interstellar body photographed from Mars itself. Every scrap of data mattered, because there would be no second chance. In late-night discussions, astronomers began using a phrase that hadn't been spoken aloud for decades: coordinated caution. It describes what happens when multiple research groups agree, sometimes implicitly, to hold their results until everyone has compared them. The logic is simple. If one team reports something extraordinary and another sees nothing, the inconsistency can cause confusion or panic. Better to wait, to align, to speak together. Still, that explanation didn't satisfy everyone. Some scientists whispered that the silence felt too absolute. They pointed to previous joint missions, like the detection of phosphine on Venus, or the methane plumes on Mars, where agencies collaborated yet still communicated openly. This, they said, was different. There was no acknowledgement, no shared framework, just a mutual absence. In the halls of online astronomy forums, theories multiplied like stars. One idea was pragmatic. Maybe the data were corrupted by radiation. Mars's environment is notorious for electronic interference, and an interstellar object moving at 67 kilometers per second might produce light too variable for standard calibration. Another theory was political, that national agencies wanted to coordinate a shared announcement after the US shutdown lifted. But there were subtler possibilities too, scientific ones that lived between the lines. Some researchers suspected that the agencies had seen something that required interdisciplinary analysis. If the object's spectral signature was ambiguous, if it included compounds or emissions outside known cometary models, it might take months to disentangle. Others wondered if 3i Atlas's brightness fluctuated rhythmically, hinting at rotation or reflection. Such periodic signals can mimic artificial beacons in early data before being ruled out. If that happened, it would explain the silence. No one wants to announce a mystery that turns out to be sunlight glinting off ice. Still, the very idea of a coordinated pause fascinated people. In a way, it represented humanity at its most cautious and most united. Scientists from nations that rarely share secrets had for once chosen the same path, to wait until they were certain. It's almost poetic to think that somewhere, in meeting rooms across continents, teams were comparing notes about the same faint visitor from the stars, their conversations unfolding in a dozen languages, all asking the same question. What exactly did we just see? There's humility in that. To pause before speaking, to recognise that knowledge can wait while truth clarifies itself. It's a rare act of collective restraint in a world that rewards immediacy. Perhaps that's what 3i Atlas had come to teach us, not through intention, but through its very nature. It reminded us that some discoveries require silence before speech, that wonder doesn't always announce itself loudly. Sometimes it arrives as a shared pause between nations, a tacit agreement to breathe before interpreting the unknown. On Mars, meanwhile, the object drifted on. Its faint coma shimmered, touched by sunlight and thin wind. No camera blinked. No spectrometer hummed. All instruments had turned back to their scheduled tasks. But in the memory banks of 7 machines and 4 agencies, its trace remained. A quiet whisper of data waiting to be fully understood, and perhaps that's fitting. When something crosses the gulf between stars, it deserves not applause but listening. And the silence of those days, deep, deliberate, shared, was humanity's way of listening together. The ESA report would have faded into routine news, another cautious footnote in a long list of comet observations, if not for one phrase that refused to fade. It appeared halfway through their summary, as if slipped in gently, almost too quietly to notice. Our instruments responded to unexpected situations. In ordinary circumstances, that sentence might mean anything from a minor calibration error to a brief flicker of solar interference. But here, set amid a text so careful and sparse, it stood out like a whisper in a still room. It suggested that something in the observation sequence hadn't gone as predicted. Not wrong exactly, just different. Astronomers spend years crafting those predictions. They model brightness curves, gas production rates, tail angles, solar heating, all the tiny mechanisms that determine how a comet behaves as it approaches the sun. Each model starts from a simple idea. Sunlight heats ice, ice becomes vapor, vapor carries dust into space, and light scatters off that dust. The process is graceful, governed by physics so familiar that any deviation becomes immediately visible. So when ESA said unexpected, it implied the object had refused to follow the script. No numbers were given, no graphs, no timestamps. Only that phrase, unexpected situations. It was the kind of sentence that drives scientists to read between the lines. Perhaps the brightness changed too fast, or the direction of outgassing shifted suddenly, as if the jet of material had moved. Or maybe the coma's shape defied the usual symmetry, stretching not behind the nucleus, but ahead of it. Each possibility whispered a different kind of strangeness. Inside the ESA Operations Center, engineers likely understood immediately what those words meant. Every spacecraft keeps meticulous logs, voltages, angles, exposure times. If the instruments responded, that suggests they had to adjust mid-observation. Something in the data triggered corrections or caused software to flag anomalies. Machines only respond when the expected signal fails to arrive. It might have been a simple mechanical reflex, like a telescope's tracking system compensating for unmodelled motion. But what kind of object makes a spacecraft recalibrate in the middle of its run? 3i Atlas wasn't supposed to be near enough to disturb anything. Its gravity was negligible, its magnetic field non-existent. The only force it could exert was light, and yet, something about it had apparently confused the sensors designed to measure that light. If the object's trajectory shifted, that would explain a lot. Even a tiny deviation from its predicted path could have rippled through the algorithms. ESA's software would have expected a certain pixel coordinate, a certain brightness curve. If 3i Atlas veered slightly, or changed brightness mid-exposure, the result would be those unexpected situations. What could cause that shift? Natural possibilities came first. Asymmetric outgassing, rotational flicker, a jet erupting from a new fissure on the surface. Comets do change shape as sunlight hits them unevenly, but these tend to evolve over hours or days, not seconds. To trigger instrument adaptation, the change must have been immediate, something dynamic, not gradual. Some analysts suggested solar wind interference. Mars sits near the Sun's line of magnetic tension, and charged particles can disrupt imaging when they collide with a detector. Yet if it were just solar wind, every spacecraft in orbit would have reported similar disturbances. They didn't. The unexpected nature seemed unique to the instruments observing 3 Atlas itself. That focused attention back on the object. To understand how sensitive such measurements are, imagine shining a laser pointer at a falling snowflake from kilometers away and noticing its spin. That's roughly the scale of precision ESA's cameras handle daily. For something to confuse them, it has to move, or behave, in a way light itself can't easily describe. One theory began circulating quietly in the following days, never officially acknowledged. Maybe 3i Atlas wasn't tumbling randomly. Comets rotate, yes, but their rotations are irregular, shaped by uneven jets and impacts. This object's brightness variation, though faint, seemed patterned, almost periodic. That kind of stability is rare for natural fragments. Some astronomers compared it to Oumuamur's peculiar light curve years earlier. Smooth, repeating, more like the spin of a balanced object than a jagged rock. ESA didn't say this outright. They only noted that their exposure models needed adjustment during the observation, which may indicate rotation or variable albedo. Variable albedo, a polite term for uneven reflectivity. It could mean patches of different material, or something more deliberate, like surfaces aligned in precise geometry. Theories multiplied. But ESA kept silent beyond that single phrase, and perhaps rightly so. Speculation can outpace data faster than light itself. The scientists involved would have been wary of fueling narratives that stretch beyond evidence. Still, in the quiet community of comet observers, the phrase unexpected situations took on a life of its own. It appeared in late-night podcasts, journal editorials, even graduate seminars, not because anyone thought it meant artificial, but because it represented something rare, a moment when nature seemed to hesitate between explanation and wonder. There's something profound about that hesitation. When a spacecraft billions of kilometers from home adjusts its gaze, confused by the light of a visitor from another star, we're reminded that technology and mystery still coexist. Our machines are extensions of our curiosity, but not its replacement. They stumble just as we do when confronted with something truly new. In that sense, 3i Atlas gave us more than data. It gave us humility. It reminded us that even after a century of exploring the heavens, there are still lights that surprise our instruments, still motions we can't fully model, still silences that mean more than noise. ESA's engineers fixed their systems, reoriented their sensors, and continued to track the object as best they could. But that phrase, unexpected situations, stayed behind, haunting, gentle, unresolved. It became a symbol of our smallness in a vast, still unfinished universe. Perhaps one day, when the full data are released, we'll find the anomaly was nothing more than sunlight glinting off uneven ice, a trick of geometry and heat. Or maybe, buried in those logs, there's something stranger, a moment when an interstellar traveller, millions of kilometres away, flashed back just a little differently, as if aware of being watched. Whatever the truth, that tiny pause in our instruments reminds us of the same lesson every cosmic visitor seems to teach. The universe is never fully predictable, and wonder, even now, can still take us by surprise. When ESA finally published their carefully worded report, many forgot that the first image had not come from orbit at all, but from the dusty surface of Mars itself. Perseverance's SkyCam had been the first to spot 3i Atlas, long before the agencies turned their larger instruments toward it. That photograph, simple and almost accidental, remained the most intimate of all. It was a machine built by human hands, standing alone on another world, lifting its camera into the soft Martian dawn and catching a faint moving light in the sky. In those few frames, a story far bigger than Mars unfolded. It wasn't just about one object or one observation. It was the moment two worlds became one vantage point. For the first time, a planet other than Earth had joined in the act of interstellar observation. Mars, silent for eons, had looked up. Perseverance's upward-looking camera, the small SkyCam mounted on its meteorological mast, wasn't meant to search for comets. It was built to study weather, dust movement, clouds, the scattering of sunlight through the thin reddish air. But like all instruments, it watched more than it was designed for. The images it captured on October 2nd were later reprocessed by NASA engineers to reveal motion, tiny, almost imperceptible changes in brightness that showed the object shifting across the frame. Each pixel of movement corresponded to thousands of kilometers of real distance. That confirmation mattered. It meant the object wasn't a reflection or a sensor glitch. It was out there, moving against the Martian sky, exactly where calculations said it should be. No illusion, no artifact, just a traveller crossing another world's horizon. For those who work with planetary imaging, there's a quiet awe that comes with moments like this. A camera that's seen only dust and rock suddenly catches something alive in the sky. Something not of that planet, not of this solar system, but passing between both. If you could stand there beside the rover, you would have seen nothing at first, just the dull salmon haze that hides the stars. But as the camera's lens gathered exposure after exposure, a line began to form. A faint glowing thread drawn across the heavens. It looked less like a comet and more like a scar of light. Soft-edged, its motion subtle but undeniable. Astronomers at Harvard and Caltech later examined the brightness profile of those frames. They noted that the shape was slightly elongated, perhaps due to motion blur from the long exposure, or perhaps the object itself was stretched cigar-like, as Oumuamua had been. Even more intriguing were the hints of green fringing at the edges of the streak. Avi Loeb, known for his cautious curiosity, suggested it was likely a chromatic artifact, a colour separation caused by the rapid motion of the object during the image stacking process. But others, like Dr. Horace Drew in Australia, disagreed. He pointed out that the pattern of a white centre and green edges didn't match the spectral response curves of the SkyCam's filter. In his view, the green hinted at something physical, perhaps an emission line in the nickel or magnesium range, metals that sometimes glow under extreme solar excitation. It was a debate without resolution, but full of quiet excitement. Even the disagreement showed how alive the data still were, how much curiosity they stirred. There was something comforting about that, a reminder that even in the age of robotic explorers, discovery still involves human wonder. The Skycam's data log showed that the image was taken near local noon. That timing is odd. Most astronomical imaging avoids daylight when scattered sunlight overwhelms faint stars. Yet even under such glare, 3i Atlas shone bright enough to register. That suggested a strong reflectivity, or albedo, perhaps metal-rich, perhaps coated with volatile ices shimmering under solar radiation. If the green glow was real, it could indicate oxidized nickel or carbon dioxide excitation, both unusual but not impossible in an interstellar comet. The data packet containing that image travelled 225 million kilometres back to Earth, relayed through the Mars orbiters and the Deep Space Network. When the engineers in California first opened the file, they likely saw nothing extraordinary, just another calibration frame. But as the object's trajectory became known, someone noticed that the faint line matched the predicted position of 3i Atlas. It was pure coincidence that the rover happened to be facing that part of the sky. Coincidence, or something that felt like it. The odds of it being visible in that exact direction, at that exact moment, were small. Mars's rotation, its orbit, the rover's fixed field of view, everything had to align within a narrow window of minutes. It was as if the universe had leaned slightly toward us, allowing one glance before moving on. After that, the Skycam continued to operate normally. No second capture was recorded. The object moved beyond the horizon and into interplanetary space. Still, that single image became one of the most important of the decade, not for what it revealed, but for what it represented. It marked the first interstellar detection ever made from the surface of another planet. That sentence alone feels like a turning point in human history, though it came quietly, tucked inside a technical memo. When you think about it, the poetry of that moment is staggering. A machine built on Earth standing on Mars saw something from another star, 3 worlds connected by a single thread of light. And in that connection lay everything we've ever hoped for in exploration: chance, precision, and a little mystery. The engineers later enhanced the image, adjusting exposure and alignment. The elongated white streak became clearer, like a brushstroke against a fading pink canvas. Some compared it to the trail of a meteor, though its position ruled that out completely. Others saw resemblance to an ion plume, the thin, glowing exhaust of a spacecraft engine. It was probably neither, but in the grain of that image every possibility seemed alive. Even the rover's name, Perseverance, felt symbolic. It had endured storms, power losses, long silences, and yet there it was, bearing silent witness to something drifting through our neighbourhood from a time before Earth was born. Perhaps one day, that image will hang in museums beside the Apollo Earthrise or the Pillars of Creation. Not because it's beautiful, it isn't, but because of what it says about perspective. That we are no longer confined to one sky. That even in the faint hum of a Martian afternoon, the universe still sends visitors worth noticing. Somewhere, billions of kilometres away, 3i Atlas continued its path. It would never know it had been seen. But we, fragile and curious, would always remember the day another planet lifted its eyes to the cosmos and saw something passing by. The photograph from October 2nd was only the beginning. 24 hours later, during the object's closest approach to Mars, every instrument we had in that region was watching. It should have been the moment of clarity, the day when 7 spacecraft caught the best, sharpest look at an interstellar visitor humanity had ever seen. But instead, the world received nothing. NASA's raw image feed, usually updated with mechanical precision, stopped. The Perseverance archive, which posted dozens of new photos each Martian day, fell silent. So did the updates from Mars Reconnaissance Orbiter. so did the routine thermal readings from Odyssey. For one day, October 3rd, our robotic presence around Mars seemed to blink. Those who follow the data streams noticed immediately. Astronomers have browser tabs open to these archives every morning. They refresh them over coffee, watching the latest horizons arrive from another world. When the pipeline stops, it's as visible as a heartbeat skipping. The pause lasted longer than anyone expected. Hours turned into days, and as the gap widened, so did speculation. There were rational explanations. NASA's internal servers could have been caught in a queue, slowed by the government shutdown that had furloughed thousands of employees. Data from Mars often pile up before they're cleared for public posting. Transmission schedules can collide. Orbiters may prioritize relays for science packages instead of image uploads. Those things happen. But even with delays, raw images don't vanish. They wait in line, then appear. This time they didn't. Perseverance's automated system was designed to bypass human review. Every frame, regardless of content, is transmitted directly to Earth and published to NASA's open database. That transparency is part of its design philosophy. Data belongs to everyone. So when images from Sol 1643, the date corresponding to October 3rd, failed to appear, researchers knew something was different. The automation hadn't failed. Someone had interrupted it. It wasn't malicious. It never is. Most likely someone flagged the data for internal review. But what makes an engineer stop an automated flow of public images? Only one thing: when a frame contains something that needs to be understood before it's shared. Maybe the exposure glitched, showing artifacts that could be misinterpreted. Maybe light from the sun caused reflections or halos that mimicked shapes. Or maybe, just maybe, the object didn't look like it was supposed to. Some insiders whispered that the images from October 3rd were under evaluation, a phrase that means less than it sounds, but also everything. It implies that the data were valid, just not yet explained. That simple difference separates a malfunction from a mystery. The timing couldn't have been more striking. October the 2nd, a faint but real image of Three Atlas in the Martian sky. October 3rd, silence. October 7th, ESA's safe fuzzy dots released to the world. It felt like the story had inhaled and never exhaled. If you imagine Mars on that day, it helps to think in scale. The object was about 30 million kilometers away. Close, but still a vast gulf. Even at that distance, the combined instruments around Mars could resolve more than any telescope on Earth. Mars Reconnaissance Orbiter's high-rise camera, designed for mapping the planet's dunes and cliffs, could theoretically distinguish structures as small as 30 kilometers at that range. Enough to outline shape, not detail. Enough to tell if something was spherical, oblong, or fragmenting. And yet, nothing. No images, no charts, no press briefings. For planetary scientists, this was frustrating but familiar. Big discoveries rarely arrive in a single moment. They're built layer by layer, data by data. Still, the absence of even a placeholder acknowledgement was unusual. NASA has published blurry, uncertain data before. It's standard practice to release first, interpret later. Holding back requires consensus, and consensus across multiple agencies takes coordination. That coordination itself became part of the mystery. China, usually quick to showcase its Mars program, said nothing. The UAE, often transparent with its Hope orbiter, was silent. ESA released only faint dots, avoiding any claims. It was as if everyone had agreed not to blink until someone else did first. Behind closed doors, scientists likely exchanged data privately. There would have been encrypted meetings, shared cross-calibrations, long nights comparing spectra and signal-to-noise ratios. Not because anyone was hiding evidence, but because none of them wanted to misinterpret it. To call something artificial when it's not, that's the kind of mistake science never forgives. Better to say nothing than to say too much. Yet outside those labs, silence felt different. It became its own phenomenon, louder than any announcement. News outlets began to speculate, forums filled with diagrams and conjecture. Some said the agencies were waiting for confirmation that the nickel anomaly, detected earlier by Earth-based telescopes, was real. Others thought the object might have split apart, or changed trajectory. And a few wondered if the missing images showed something geometric, something too strange to explain without proof. Those rumours spiralled fast, but underneath them was a deeper truth. The world had grown used to instant answers. When information slowed, imagination took its place. Perhaps that's the most revealing thing about this story. The silence didn't prove a conspiracy. It proved our impatience with uncertainty. We're a species that demands clarity from a cosmos that almost never gives it. 3 Atlas reminded us that discovery isn't always a spectacle. It's a long, cautious unfolding, sometimes too slow for our restless hearts. Still, there's something poetic about those missing frames. They became negative space, like the dark matter between galaxies, unseen, yet shaping everything around them. Every hypothesis, every debate, every hope for what 3 Atlas might be, all of it was pulled into the gravity of that absence. And maybe, just maybe, that's how great mysteries begin. Not with revelation, but with pause. A breath caught between data points. A single day of silence from a red planet, holding a secret that may one day be revealed in the quiet hum of a hard drive, waiting for the right eyes to open it. When the images stopped, 2 explanations competed quietly among scientists, one mundane, one extraordinary. The first was technical, tied to the slow mechanics of bureaucracy. Maybe the Mars data pipeline had simply clogged under the weight of the shutdown. The second, far less comfortable, was that the missing frames contained something that demanded coordinated analysis before release. Something that needed, as one astronomer put it, global verification. It's easy to forget how many people touch a single image from Mars before it reaches the public. Engineers manage downlink priorities, programmers validate checksum integrity, calibration specialists filter cosmic ray noise. Each image is processed by layers of automation, then occasionally paused by human hands. If those hands stop the flow, there's a reason, an anomaly that demands context. The Perseverance rover doesn't know when it witnesses history. It simply photographs what's above it, transmitting every few minutes like a breathing rhythm. On October 3rd, during the window of closest approach, it should have continued that rhythm. Yet the sequence abruptly ended mid-cycle, and for more than 4 sols, the length of Martian days, no skyward image appeared again. For those who follow the rover logs, that was a puzzle. Not because gaps never happen, but because this one aligned with a moment when the whole of human astronomy had been watching the same object. That timing was almost poetic, almost deliberate. Speculation took many shapes. Some said the rover's skycam had overheated, forcing a reboot. Others believed the data packets were flagged for priority analysis, hand-inspected for calibration issues before posting, and a smaller group, less comfortable with coincidence, wondered if the captured frames revealed something unexpected in the motion of 3 Atlas itself. If the object's brightness fluctuated rapidly, if its light pulsed or reflected in repeating intervals, the effect would appear in consecutive exposures as an artificial rhythm, a sequence of flashes that could, in theory, resemble a signal. That idea drifted like a rumour through online astronomy circles. No one claimed evidence. No one denied the possibility either. Avi Loeb, always careful, was asked about the missing data in a brief interview. He smiled and said, "Sometimes silence is just data that hasn't spoken yet." It was a poetic way to remind people that absence doesn't mean conspiracy. It can mean precision. But still, his phrasing carried an undertone of curiosity, as if he too sensed that this particular silence had texture. NASA, of course, said nothing. Press inquiries received polite acknowledgements but no new information. Images will be released when verified, one representative wrote. Verification, an ordinary word suddenly heavy with implication. It's worth remembering how verification works in deep space observation. When an image reveals something unexpected, you don't rush to publish. You compare it against independent sensors. You ask, did another instrument see the same thing? Is it aligned with predicted coordinates? Could it be cosmic ray interference? Reflection from a satellite or camera motion? Each possibility must be ruled out before an anomaly becomes a discovery. Now imagine that process multiplied across 7 spacecraft from 4 different nations, each one collecting data under different exposure settings, different filters, different times. The comparison alone would take weeks, perhaps months. And while those weeks passed, the world waited, inventing its own explanations. In that sense, the missing data became an experiment in patience. It forced everyone, scientists, journalists, and dreamers alike, to sit with uncertainty. And in doing so, it reminded us of something cosmic in scale, that not all questions fit within our schedules. Still, what could require global verification? One possibility was chemical. If the spectrometers aboard Mars orbiters detected compounds that didn't match natural comet chemistry, that would warrant review. Nickel without iron, as ground telescopes had already suggested, would be one such signature. Carbon dioxide dominance could be another. If multiple agencies confirmed those anomalies, the implications would ripple far beyond Mars. Another possibility was geometric. If high-resolution cameras captured shapes that implied structure, edges, planes, regular symmetry, the data would need extraordinary scrutiny. The human mind loves patterns even in randomness. A single glint of sunlight on an oddly angled surface can trigger speculation for years. Astronomers have learned that lesson many times, and yet structure isn't impossible in nature. Crystals form lattices, ice fractures into straight lines, and magnetic forces carve precision into chaos. If 3i Atlas had fragmented, or if its jets had carved patterns of light, the resulting geometry could have seemed artificial at first glance. That's enough to make any space agency pause. There's also a subtler reason for silence, one of coordination rather than secrecy. When multiple nations share overlapping observations, they sometimes agree to synchronize their announcements. It prevents conflicting headlines, keeps public understanding cohesive. That's science's equivalent of diplomacy, and it's rarely quick. Meanwhile, 3i Atlas continued on its path, oblivious to our confusion. Its coma grew broader, brightening gently as it neared the inner regions of the solar system. By mid-October, it had already moved beyond the reach of Mars-based sensors. The data, whatever they showed, was frozen in time, a snapshot of one fleeting encounter. There's something haunting in that image we never saw. Somewhere, perhaps on a secure NASA server or an ESA backup array, those raw frames rest quietly. In them may be nothing unusual at all, just the blur of dust illuminated by sunlight. Or perhaps there's a trace of something else, a pattern, a colour shift, a shimmer that didn't belong. We may never know. But even if the mystery is only procedural, the symbolism lingers. A single day of missing data reminded us that our knowledge of the universe still relies on human judgment. Every great discovery passes through doubt before it becomes truth. And doubt, though uncomfortable, is what keeps science honest. Maybe one day, long after the data are finally released, we'll look back on this silence as the moment humanity remembered how to wonder without conclusion. A lesson in how to wait, listen, and let the cosmos unfold on its own time. As the days passed and the silence deepened, astronomers turned their attention from Mars to the path itself. If 3i Atlas refused to reveal its nature, perhaps its trajectory could. After all, motion is the universe's handwriting, the way gravity records intention, and the handwriting of this object was almost too precise to believe. When scientists reconstructed its orbit using data from July through early October, they found that it was nearly coplanar with the solar system, its inclination just under 5 degrees relative to the ecliptic. In cosmic terms, that's almost perfectly flat, almost perfectly aligned. For something arriving from interstellar space, such precision is nearly impossible by chance. An interstellar object can come from anywhere. The sky's a full sphere of possibilities, north, south, above, below the plane where our planets spin. Out there, gravity has no reason to aim for our narrow celestial disk, and yet, 3I Atlas slid directly into it, like a thread through the eye of a moving needle. To understand how extraordinary that is, imagine tossing a handful of grains into a whirlwind and finding one that passes exactly through a ring the size of a coin. That's the scale of improbability astronomers were facing. When they calculated it, the odds came out to roughly 1 in 200,000, a number so small it borders on deliberate, and still, the coincidences multiplied. Not only did the object align with the ecliptic, it timed its passage to graze Mars in October and approached Jupiter in March of the following year. 2 worlds rich in instruments, both positioned perfectly for observation. If this were a cosmic roll of dice, the result would have been an impossible streak of 7s. Of course, orbital mechanics are not luck. They're cause and effect. Every motion has a reason, even if the reason is distant and ancient. Some researchers propose that a stellar encounter long ago might have nudged the object into its current course, curving its path just enough to intersect our solar plane. Others argued that gravitational focusing by the Sun itself could explain the alignment, bending its trajectory inward. But those models required fine-tuning almost as unlikely as the alignment itself. Then came a hypothesis that felt stranger, but eerily plausible. What if the trajectory wasn't random at all? What if it had been chosen? This wasn't idle speculation. In recent years, the field of interstellar engineering, a small but serious branch of theoretical astrophysics, had explored how a civilization might send long-lived probes between stars. The mathematics show that the most efficient route into any planetary system is along its ecliptic plane, where gravitational assists from multiple planets can slow or capture a passing object. It's how we would do it if we could. Why waste energy diving steeply when you can skim the system's natural conveyor belt? That logic made the 5-degree tilt look less like coincidence and more like strategy. And for those willing to entertain that idea, the object's next destination, Jupiter, seemed even more suggestive. Jupiter's massive gravity well is the perfect decelerator. A passing body can use it to adjust trajectory, even become trapped. If 3I Atlas altered speed at its next encounter, it might not leave the solar system at all. Still, most astronomers resisted the implication. They pointed out that improbable things do happen. Given enough comets, enough galaxies, and enough time, the universe produces coincidences. Statistical miracles are inevitable in an infinite stage. And yet, skepticism doesn't erase curiosity, it just refines it. Some researchers began comparing 3 Atlas to its predecessors, Oumuamua in 2017 and Borisov in 2019. Oumuamua had been elongated, fast and strangely reflective, its acceleration unexplained by outgassing. Borisov, on the other hand, behaved exactly like a comet. 3 Atlas fell somewhere in between, too structured to ignore, too ambiguous to define. Its orbit seemed to inherit a little of both, the mystery of Oumuamua's precision and the gentler coma of Borisov's natural decay. As calculations continued, another detail emerged: its mass. Based on observed brightness and assumed reflectivity, estimates placed it near 30 billion tons. That's enormous for a comet, yet compact for a fragment of planetary debris. It was as though the object belonged to neither category fully, a visitor caught between 2 definitions, both too small and too massive depending on your point of view. Avi Loeb published a quiet note on the Harvard site, suggesting that such a trajectory invites closer scrutiny. He didn't say artificial. He didn't need to. The language of probability spoke for itself, and so the question took shape, softly but firmly. Was 3I Atlas simply a traveller from another sun, flung here by gravity's aimless tides, or was its path the product of design? If it were engineered, even passively, it would mean someone out there understood not only our solar geometry but our curiosity. To pass near two inhabited planets within a few months of each other isn't just a flight path, it's an invitation. Even so, the scientists most intrigued by this idea treated it with restraint. In the halls of observatories, over dim coffee at 2 a.m, they'd say things like, "It's probably natural, but if it isn't, this is exactly how it would look." That kind of conditional wonder is the heartbeat of astronomy, open to astonishment, anchored by caution. What makes this story so compelling isn't certainty. It's the balance between logic and awe. The orbit of 3I Atlas doesn't break any laws of physics. It obeys gravity, momentum, and light pressure exactly as it should. But within those laws, it dances with improbable grace, a choreography so fine that it blurs the line between chance and choice, and perhaps that's what draws us most deeply to it. Because whether by nature or intention, this interstellar traveller seems to know exactly how to move through the silence, just close enough to be seen, just mysterious enough to make us question what seeing even means. If one day we discover it wasn't random, that the 5° tilt was deliberate, that the encounters with Mars and Jupiter were planned, it would change everything about how we think of life in the universe. But even if it's only coincidence, it's the kind of coincidence that wakes us up beneath the stars and reminds us that the cosmos still has its own quiet wit. That somewhere between geometry and mystery there is room for wonder to live. By mid-October, the debate had hardened into 4 main theories, each elegant in its own way, each incomplete. They were less like competing answers and more like mirrors, reflecting what different kinds of scientists hoped, feared, or believed about the universe. In that sense, 3I Atlas had become something more than an object. It was a Rorschach in the sky. The first theory was the most traditional, a natural comet from another star. It fit the simplest story, a frozen fragment ejected long ago from its home system, flung across interstellar distances until gravity pulled it through ours. Its coma, its motion, its soft tail of dust, all of it could be explained by sunlight warming volatile ices. But even this straightforward idea stumbled on small details. Its early outgassing, its carbon dioxide dominance, its brightness curve, none of these quite matched the usual models. It was as though nature had followed familiar rules but improvised the melody. The second theory went further, an exotic interstellar body, not a comet at all, but something forged under unfamiliar conditions. Perhaps it was a fragment from a supernova remnant, or a metallic shard from the crust of a long-dead planet. Its nickel-heavy emission, coupled with the absence of iron, pointed toward chemistry rarely found in natural bodies. Nickel can condense without iron only in environments of intense radiation and specific cooling rates, places like the outer layers of dying stars. If that were true, then 3I Atlas wasn't a comet or probe, but a relic. A cosmic fossil hurled through time, carrying the chemical accent of another galaxy's end. The third theory was bolder, an ancient probe, not necessarily active, not transmitting, not glowing with intent, just an artifact. A long silent craft left adrift by a civilization now gone. Perhaps it had once mapped other systems, or once was meant to. Its orbit, so carefully aligned, might have been the lingering echo of its mission design. In this vision, 3I Atlas was a bottle drifting on the interstellar tide, its message lost, its sender forgotten. Even inert, its precision felt purposeful. To believe this theory didn't require fantasy, only the humility to imagine that we are not the first to look outward. The fourth theory was a hybrid, a comet with an artificial core, a fusion of natural and deliberate, of ice and intention. Perhaps some civilization had hidden its machinery inside a cometary shell, knowing that nature provides the best camouflage. The outer layer of dust and frozen gas would not only protect it, but also disguise it, making it appear perfectly ordinary to distant eyes. When sunlight warmed the surface, jets of vapour would behave exactly like a comet's, while the core within could remain intact, insulated, unseen. It's a hypothesis that belongs to science fiction, but then again, science fiction has a habit of becoming science history. Astronomers didn't declare allegiance to any of these ideas. Instead, they treated them like constellations, patterns of possibility drawn across the dark. Each explained part of what was observed, but left shadows of uncertainty between its stars. The nickel without iron signature still nagged. So did the perfectly aligned orbit. So did the unusual forward-facing jet. Recorded faintly in ESA's brightness models, a plume not trailing behind like a comet's exhaust, but emerging from its leading edge. That shouldn't happen in a natural body, at least not without a strong rotational offset. Unless, of course, the jet wasn't simply venting, it was directional. But here's where astronomy's humility shines brightest. Rather than declare intent, scientists searched for natural analogues. They cited Comet Encke, which occasionally exhibits forward jets due to solar wind deflection. They referenced 67P Churyumov-Gerasimenko, which the Rosetta mission found leaking gases from odd crevices that produce strange thrust patterns. Space, they reminded everyone, is creative enough without our help, and yet even the cautious ones admitted the pattern was peculiar. As 3i Atlas drifted inward, the orientation of its jet appeared to adjust ever so slightly, as though maintaining its alignment toward the sun rather than away from it. Solar radiation pressure could cause that, so could rotation. But the mathematics didn't settle easily. The simplest natural models failed to fit the data cleanly. So the mystery remained, stable, silent, and utterly indifferent to our attempts at definition. Outside the official papers, imagination roamed free. Artists sketched shimmering metallic cores wrapped in vapour. Podcasts debated whether interstellar objects might carry dormant technology, waiting for stellar warmth to wake them. Documentaries resurrected the ghost of Oumuamua, drawing parallels between the two. And through it all, astronomers kept returning to the same grounding truth. Every mystery begins as nature misinterpreted. Only patience separates wonder from mistake. Still, in late October, a few voices began to notice one more coincidence: the line of sight. As 3i Atlas moved inward, its projected path intersected a narrow region of the sky connected with an old riddle, the coordinates of the 1977 WOW signal. That brief radio burst, recorded by the Big Ear Observatory in Ohio, had never been explained. It came from no known satellite, no planetary reflection, no atmospheric event. It simply appeared for 72 seconds, then never repeated. The direction: a patch of space near Sagittarius, precisely where 3i Atlas now seemed to align. No one suggested causation seriously, but the coincidence was eerie, a kind of poetic rhyme across decades, different wavelengths, different instruments, yet connected by geometry and curiosity. The scientists smiled at the comparison, but the public seized it eagerly. For many, it was too beautiful to ignore, a signal once heard, and now, 48 years later, a visitor crossing the same corridor of space. Coincidence or not, the alignment deepened the object's myth. It reminded people that our instruments, for all their precision, are also storytellers. They see what we teach them to see, and when the universe presents patterns, we can't help but listen for meaning. As October faded, 3i Atlas continued toward the sun, trailing questions like a comet's tail. Was it alive with chemistry or asleep in silence? Was its path natural or chosen? Would it pass harmlessly or stay? No one could say. But one thing had become certain. This object, whatever it was, had captured not just our data, but our imagination. It had turned astronomers into poets and skeptics into dreamers, binding us all to that timeless wonder that begins every act of science, the willingness to ask what if and mean it. As October deepened, 3 Atlas moved into a region of space where sunlight began to change its personality. The gentle warmth that had awakened the comet's surface gave way to fierce radiation. The object was now falling inward toward its perihelion, the point of closest approach to the Sun, and the light that touched it was 10 times stronger than what it had felt near Mars. Normally that would be the moment of revelation. Comets bloom under heat. They shed their frozen veils and display their cores. But for 3I Atlas, the timing carried a quiet irony. Just as it entered the most illuminating part of its journey, it slipped from view. From our vantage point on Earth, the Sun had claimed it. The geometry of orbits had turned against us. Between October 29th and late November, the object would pass behind the solar disk, entering a window of invisibility. Even the most powerful space telescopes, the James Webb, the Hubble, the European Solar Orbiter, could not follow it there. It was like watching a traveller step behind a curtain of light, leaving only questions in their wake. Astronomers call this period solar conjunction. It's a common phenomenon, a simple matter of alignment. When the Sun stands between us and whatever we're observing, its glare overwhelms the signal. For deep space communication, it's a blackout zone. For curiosity, it's a test of patience. We could no longer see the visitor at all, not directly, not even in radio frequencies. The Sun's corona drowned everything in noise. This wasn't just a technical inconvenience, it was symbolically perfect. The moment of greatest mystery coincided with the moment of blindness. We were forced to imagine what might be happening rather than witness it. Before the silence began, astronomers had debated what the Sun's heat might do to the object. Some predicted a breakup. Comets often fragment under thermal stress as trapped gases expand violently inside them. Others thought it would survive intact, its dense material holding together through the fiery approach. But a third group wondered if the close pass might change its orbit in a more subtle, more permanent way, by bending it just enough to keep it inside the solar system. That last idea was quietly unsettling. If 3C Atlas slowed even slightly during perihelion, perhaps through mass loss or solar drag, it might not escape. Instead, it could become bound, a new, faint wanderer captured by the Sun, destined to return again centuries from now. A captured interstellar object, a visitor turned resident. It would be the first of its kind ever known. Such a capture would make sense of many peculiarities: the low inclination, the near-perfect ecliptic entry, even the alignment toward Jupiter. All could be interpreted as the conditions of a planned insertion, or at least an optimized one. And if the object did indeed slow enough to stay, its next visible orbit might bring it into the inner system again, perhaps near Earth, perhaps not for hundreds of years. But no one could confirm any of it yet. The conjunction meant the object had vanished behind the veil of light. For the next month, humanity could only wait while the Sun itself held the answer. The timing was almost too poetic. A mystery born in darkness, drawn into glare, now disappearing into pure radiance. It was the cosmic equivalent of a candle being blown out by its own flame. Meanwhile, radio astronomers tried indirect approaches. By monitoring the Sun's corona for reflected signals, they hoped to detect faint perturbations caused by the object's presence. It was like listening for an echo behind a waterfall. Some observatories thought they heard fluctuations, tiny shifts in brightness across the corona, but the data were inconclusive. It could have been coincidence or the signature of solar flares. In the language of science, it was simply noise, but in the hearts of those who waited, it was music just out of reach. For the general public, the conjunction became a perfect metaphor. Social media posts spoke of the hidden visitor, of the ghost behind the Sun. Artists painted it as a glowing ember being consumed by fire, or as an eye closing against too much light. Even mainstream outlets used poetic phrasing. 3 Atlas enters the solar curtain. A celestial guest vanishes into daylight. The story had transcended data. It had become myth. Yet beneath the poetry, astronomers felt the gravity of the moment in a more literal sense. The sun's pull was everything now. At 67 kilometers per second, the object was racing through the inner system, its fate determined by minute details of density and angle. If its core was porous, it might burst apart. If metallic, it might hold together and loop into an elliptical orbit. If both, ice and metal, it might split cleanly, one part captured, the other flung outward forever. Each scenario was running through simulation labs across the world. Computers at JPL, ESA, and the Chinese Academy of Sciences spent weeks modelling variations. None agreed perfectly. Some predicted total disintegration. Others showed stable capture within the sun's gravitational boundary. A few even suggested an extreme outcome. The object's acceleration pattern could produce a trajectory so precisely altered that it would mimic controlled braking. That last model was quietly set aside. It fit the data but required intent. For now, there was only waiting. Each day, solar monitors recorded the same blinding flux, the same unbroken hum of energy. And somewhere within that brilliance, invisible and mute, 3I Atlas was changing. Perhaps it was burning away, a final burst of vapour scattering across the corona. Perhaps it was holding steady, its nickel-rich shell reflecting light without melting. Or perhaps something subtler was happening, an alteration of spin, a deflection so slight no telescope could yet measure it. We would not know until it emerged from behind the sun in late November. When it did, its brightness, or its absence, would tell the story. Until then, the world's telescopes pointed elsewhere. The astronomers waiting like listeners who know the next note is coming, but not when. And as nights passed, the universe felt unusually quiet, as though holding its breath with us. The interstellar traveller had vanished into light, leaving us to wonder whether we'd ever see it again, or whether it had chosen the perfect hiding place inside the brilliance of the star we take for granted every day. When the object disappeared behind the sun, a strange kind of calm fell over the scientific community. For the first time in weeks, there were no new images to analyse, no anomalies to debate, no press releases to decode. Only models, numbers running endlessly in silence. And in that stillness, astronomers began to look inward, reflecting not just on 3I Atlas, but on what such a moment says about us. It's easy to forget that astronomy is as much philosophy as physics. Every observation is a mirror held to human patience. We stare at the heavens knowing most of what we seek will remain hidden, and still we watch. We model light we cannot touch. We measure shadows that no longer exist. We speak in predictions because direct sight is a privilege the cosmos rarely allows. The sun itself became part of the drama. Its face was restless that month, solar flares arcing out like ribbons, coronal mass ejections rippling through the solar wind. Each eruption briefly distorted the region where 3I Atlas would have passed. Even if the object had survived intact, those waves of charged particles could have changed everything. Its spin, its path, perhaps even its structure. Some joked that the sun was testing it, like a gatekeeper deciding whether the visitor could stay. But deep in that quiet period, one more discovery slipped through. A set of ground-based spectroscopic readings from before conjunction, gathered by an array in Chile, revealed a new twist, a faint emission line matching pure nickel, but still no trace of iron. The line was narrow, sharp, unmistakable, and its intensity implied not dust or mineral reflection, but glowing vapour, atoms excited to radiate by energy input. Something had heated that nickel enough to make it shine, yet somehow the iron atoms that should have accompanied it were missing. On Earth, nickel and iron are born together. They are siblings in the forge of supernovae. Every known natural process that produces nickel produces iron in equal or greater amounts. To separate them requires something artificial, a refining process, an industrial touch, and that, more than the orbit or the silence, became the most haunting detail of all. Scientists tried to find natural mechanisms that could explain it. Perhaps micro-impacts had selectively released nickel compounds. Perhaps magnetic sorting in the interstellar medium had stripped away iron grains. Perhaps the spectral calibration was off. All were plausible, but each felt a little strained, like an excuse searching for comfort. For the first time, even the most cautious voices hesitated. They didn't say alien, of course. They never do. But phrases like unusual metallurgical behaviour and unexplained compositional isolation began to appear in papers and conference notes. The vocabulary of wonder had returned, dressed in academic restraint. It is worth remembering that humanity has seen anomalies like this before. Meteorites rich in pure nickel have occasionally struck Earth, rare, dense, magnetic relics from the cores of ancient worlds. But those still contain traces of iron, locked together in atomic companionship. To find nickel alone, gleaming in the darkness of space, is something else entirely. There's a certain poetry in the idea that our first true interstellar visitor might carry metal once refined by unknown hands, or unknown physics. Maybe it wasn't technology at all. Maybe the universe itself, vast and clever, had found a way to separate elements through forces we don't yet understand. In that possibility lies both humility and hope. Meanwhile, simulations of the object's orbit during perihelion continue to diverge. Some showed a stable return path that would bring 3I Atlas back into view by early December. Others predicted complete disintegration under solar stress, but a few, just a few, suggested a different kind of outcome. They showed a trajectory bending subtly, curling inward in a way that hinted at deceleration. If that model were true, the object wouldn't escape. It would remain trapped within the sun's gravitational influence, perhaps orbiting on a long, slow loop that would bring it back toward the outer planets in decades or centuries. If captured, its new home would likely be beyond Jupiter, in the quiet zones where sunlight fades and comets sleep. There, amid the cold dust of the Kuiper Belt or even the Oort cloud, it could drift indefinitely, a foreign seed planted in our system. To imagine it resting there, faint and silent, is strangely comforting. A reminder that even travellers from other stars sometimes find a place to stay. But some astronomers weren't ready to believe in rest. They pointed to a peculiarity in the data from October 25th, the last day before the conjunction. The object's light curve had shown a rhythmic flicker, subtle but consistent, every 16 minutes. It wasn't strong enough to be a signal, but it wasn't random either. Rotation could explain it, but the pattern was steady enough to feel deliberate. It might have been coincidence, or a structural resonance, or something we can't yet name. The human mind is wired for pattern. We find rhythm in randomness, faces in clouds, messages in noise. And yet, sometimes the patterns are real. Science begins when we ask which is which. In a dim office in Pasadena, an orbital dynamics engineer put it simply, "We don't have to call it artificial to call it interesting." That phrase spread quietly through the community. It became a kind of mantra for those unwilling to surrender curiosity to fear. Because that's what science is, not certainty, but the courage to stay curious even when certainty disappears behind the sun. So the world waited again, calendars marked for November the 28th, when 3I Atlas was expected to re-emerge from the glare. Would it still be glowing? Would it even exist? Would it reappear brighter, fainter, or changed? No one knew, but telescopes across Earth and in orbit were already preparing, resetting their sensors, realigning their optics, because the moment it came back, the first photon would tell us everything, whether it had survived, transformed, or quietly slipped away into light. Until then, the night sky offered no answers, only patience, and as the days shortened and the sun's brilliance hid the object completely, it felt as though humanity had placed a single, fragile question into the heart of the star itself, waiting for the light to answer. When 3I Atlas finally emerged from behind the sun, the world of astronomy leaned forward as one. Radio observatories resumed scanning, deep space telescopes adjusted their optics, and amateur sky watchers in dark deserts turned their instruments toward the dawn. After a month of invisibility, the question was simple. Would it still be there? It was, but not quite as expected. The first detection came from ESA's solar orbiter, not in the visible spectrum, but in ultraviolet. A faint streak of light appeared just beyond the corona, cooler and dimmer than predicted, its coma smaller but strangely sharper in outline. A few hours later, Earth-based telescopes confirmed visual contact. The object had survived its passage, yet something about it had changed. Its brightness had fallen by nearly half. The coma that once glowed wide and hazy now seemed compact, tightly bound around a dim core. That alone would have been unremarkable. Comets often lose mass and shrink after perihelion. But the way it moved was new. Its tail wasn't trailing behind in the usual way. It seemed to curve forward, faintly luminous against the direction of travel. That forward curving tail puzzled everyone. It defied basic solar dynamics. Normally, solar wind pushes dust and gas away from the sun, forming a tail that always points outward. Here, the geometry was reversed. At first, scientists assumed an error. Maybe a misaligned camera or a trick of parallax. But then 3 different observatories reported the same thing, a faint pale jet angled sunward. If that was true, it meant one of 2 things. Either the dust was being magnetically deflected, an unlikely scenario requiring an internal magnetic field, or the gas was being emitted under control like thrust. No one wanted to use that word. Instead, the official language became non-gravitational acceleration anomaly, a polite way of saying it's moving when it shouldn't be. This wasn't entirely unprecedented. Oumuamua had done something similar, veering slightly from its calculated path in 2017. Back then, the explanation was that sublimating ice jets, invisible from Earth, had nudged it like microscopic thrusters. But 3I Atlas was different. Its motion was steadier, its deviation smoother, as if continuous rather than impulsive. It wasn't being pushed, it was gliding. Orbital plots released in early December showed the new trajectory bending gently inward instead of escaping. That meant a change in energy. Somewhere during perihelion, the object had lost speed. It was still moving fast, tens of kilometers per second, but now on a long, slow curve that would keep it within the solar system for years, maybe centuries. It hadn't left. It had joined. The realization spread slowly through research circles. At first, it was dismissed as a rounding error in early tracking. Then, when multiple agencies confirmed it, the mood shifted from skepticism to awe. For the first time in recorded history, an interstellar object had been captured by our sun. A wanderer from another star had become part of our celestial family. The implications were immense. Even if it were entirely natural, its mere presence meant that interstellar material could be trapped more easily than once thought. That could reshape our understanding of planetary formation, even of how life-bearing compounds spread between stars. But for some, the capture itself felt too perfect. The trajectory had decelerated, almost as if timed, the curve symmetrical, the energy loss precise. If it were random, it was an astonishing coincidence. If it weren't, well, that was a thought best kept unspoken. Still, subtle hints continued to surface. The object's rotation period, measured through photometric flicker, had changed since October. It now spun twice as fast, suggesting a redistribution of mass or torque, perhaps from outgassing, perhaps from something else. Its nickel-rich emission line persisted, though weaker. An infrared data hinted at lingering heat around the nucleus, warmer than a simple comet should be weeks after solar exposure. Nothing dramatic, just a few degrees higher than models predicted. But in the language of science, a few degrees can mean everything. Among the teams tracking it, one researcher in Spain noticed something quietly elegant. When plotted against the orbital planes of Mars and Jupiter, 3I Atlas's new path fell almost perfectly between them, like a corridor. That region is stable, gravitationally calm, dotted with Trojan asteroids that share Jupiter's orbit. In effect, it had found the most peaceful orbit possible within the inner system. Not too close to heat, not too far from sunlight. A perfect parking spot. No one called it deliberate, but more than one paper described the capture as energetically efficient, which in celestial terms means as if planned. Even the timing seemed uncanny. In the first week of December, while astronomers debated, the sun unleashed a minor flare that temporarily disrupted radio signals across Earth. When communications stabilized, the faint ultraviolet trace of 3I Atlas had shifted slightly, just enough to make tracking software blink. It wasn't much, just a fraction of a degree, but to orbital analysts it looked as though the object had adjusted its position in response to the solar wind. Natural? Possibly. Intentional? Impossible to say. For the general public, the idea of capture became the headline. Interstellar objects now orbiting our sun, read the front pages. For once, science news carried the rhythm of myth, an exile welcomed home by gravity itself. Commentators spoke of fate, of cosmic migration, of how every star must one day inherit a traveller from another. It was beautiful to think about, a piece of another sky choosing, however unconsciously, to stay. But beneath the poetry, the data told a subtler story. Captured or not, 3I Atlas was behaving like nothing we'd seen before. Its forward-facing jet, its precise deceleration, its persistence in the solar corridor, all of it suggested more than coincidence. Something about this visitor felt intentional, even if the intent was written in the language of physics rather than will. Perhaps that's what makes astronomy so haunting. Even when the universe acts without mind, its motions can look like meaning. And maybe in a way that's enough, because to watch a piece of another system settle into ours is to see connection itself made visible. A reminder that gravity doesn't separate worlds, it gathers them. As winter arrived on Earth and Mars rolled into the far side of its orbit, the object remained invisible to the naked eye, a dim ember drifting through the darkness between planets. No transmissions, no drama, just a quiet newcomer circling a quiet star. And in its silence, we found reflection, a reminder that every discovery changes us not by what it reveals, but by how much wonder it leaves behind. For astronomers, the word capture has a precise mathematical meaning. It describes when an object crosses the threshold between freedom and belonging, when its velocity, once too high to be bound by the sun, falls just enough that gravity closes its hand around it. 3I Atlas had crossed that invisible line. By every available model, it was now part of our solar system. Yet what made that realization extraordinary was not the physics, but the poetry of it. An interstellar wanderer, travelling for millions of years through the dark between suns, had entered our family of worlds and decided, by chance or by nature, to stay. It was like a single grain of sand settling into a new beach, forever changing its shoreline. Data from December confirmed the new orbit, a long ellipse extending beyond Jupiter, looping back in roughly 80 years. That meant that, if stable, this object would return in the lifetime of our grandchildren. In the grand sweep of cosmic time, it was almost an eye blink. We had not lost it to infinity. We had only begun the first chapter of its long story. Still, as with every gift the universe gives, it came wrapped in mystery. The same measurements that proved capture also revealed acceleration that made no sense. 3 Atlas was not just slowing, it was self-adjusting. The small, steady thrust detected during its post-perihelion phase hadn't stopped. Even in the calmer sunlight beyond Mars, it continued to alter speed by tiny, measurable amounts, as if guided by feedback. Natural jets could not maintain such constancy over weeks. They sputter, fade, pulse irregularly. This was smooth, sustained, deliberate in tempo if not in intention. ESA's team hesitated to publish that data, but ground-based observers confirmed it independently. A faint drift in position accumulated nightly, building into a deviation large enough to demand explanation. In conference calls, scientists began to use a new phrase, non-random vectoring. It sounded clinical, but beneath it lay something quietly thrilling. 3i Atlas appeared to be adjusting its course in a way no comet or asteroid ever had. At first, they searched for natural causes. Could the tail's forward curvature be producing drag? Could uneven thermal release from nickel-rich crusts act like slow jets? Could electromagnetic coupling with the solar wind generate a Lorentz torque? Each idea explained a fragment of the data, but none explained all of it. Every time one inconsistency was solved, another arose like ripples that never stopped. Meanwhile, infrared instruments continued to detect a faint warmth around the nucleus. Not heat like fire, but a lingering thermal glow that refused to fade as fast as it should have. A comet's surface cools quickly once sunlight wanes, but 3i Atlas stayed several degrees warmer for weeks, as if energy were being stored or generated internally. It was not bright enough to suggest combustion or reaction, just enough to keep theorists awake at night. Some proposed exotic physics. Perhaps the nickel emission hinted at radioactive isotopes, slowly decaying elements that release steady heat. Others speculated it could be piezoelectric effects, frictional charging between metallic and icy layers, but every model demanded a precision of composition that felt almost designed. If random, it was the most elegantly random structure ever found. By mid-December, the consensus was that this was the first active interstellar capture. That phrase entered the literature quietly, but its meaning was immense. An active object meant not static, a body whose motion changed beyond simple gravitational dynamics. Active didn't imply life or technology, it merely meant interaction. But the word still carried an echo of agency, a whisper of will. The most striking feature, though, came from polarimetric studies. When sunlight scatters off dust or ice, it polarizes. Its electric field tilts in predictable ways. Natural comets show positive polarization, meaning their light waves align in a specific direction. 3i Atlas, however, showed negative polarization, light oscillating in the opposite phase. Such reflection patterns are vanishingly rare, seen only in certain crystalline metals and engineered surfaces. To the human eye, it meant the object glowed differently from anything else in the sky, as though rejecting light rather than reflecting it. That discovery rekindled debates long thought settled since Oumuamua. Back then, negative polarization had been proposed as evidence of a smooth, reflective hull-like surface, a speculation quickly dismissed as too fanciful. Now, it had returned, measurable and real. The official explanation became highly compacted regolith or metallic micrograin matrix. But off the record, even seasoned scientists admitted they'd never seen its like. In interviews, the language turned philosophical again. One astrophysicist described it this way: "Every so often, the universe shows us something that behaves as if it's paying attention." He didn't mean intelligence, not literally. He meant the uncanny feeling that certain motions seem to respond, not to us, but to their environment, with the grace of awareness, a sunflower turning toward the light, scaled to celestial proportions. And maybe that's all 3i Atlas was, a natural mechanism so finely tuned that it mimicked intent. Nature does that often. It invents elegance accidentally. From the self-ordering of snowflakes to the symmetry of galaxies, purpose arises where none was planned. The cosmos is the ultimate artist, signing its works with probability and patience. Still, the notion of mimicked intent fascinated people far beyond academia. Philosophers wrote essays about cosmic agency. Poets wrote lines about wanderers finding home. One line, shared widely online, read, "Perhaps it was never meant to arrive. It merely remembered how to fall." There's comfort in that thought, that every trajectory, human or cosmic, eventually finds its place of rest. Back at the observatories, the data kept arriving, faint but steady. 3i Atlas continued on its new orbit, moving between Mars and Jupiter, a dim spark just below naked eye threshold. Its jet had softened but not vanished. Its nickel emission pulsed faintly once every rotation, like a heartbeat no one could hear. And as winter nights lengthened across Earth, telescopes tracked it in quiet reverence. It was no longer a guest. It was one of us now, an adopted child of the sun drifting in slow, deliberate grace through a family it may never have meant to join. Perhaps one day we'll send a probe to meet it. Perhaps not. For now, it remains a story written in orbit, a reminder that even across the emptiness between stars, gravity and curiosity can find each other. And in that meeting, we're all a little less alone. By early January, the story of 3 Atlas had shifted from urgency to quiet reverence. No longer a breaking mystery, it became a slow, unfolding meditation for the global astronomy community, something between a study and a prayer. The object had settled into its new orbit, looping gracefully through the region between Mars and Jupiter. But its behaviour, even now, remained strange. Each week, observatories reported a small but measurable oscillation in its brightness. The variations were rhythmic, consistent, almost metronomic, 60 minutes apart just as before. To most, this simply confirmed its rotation period, the time it took for one full spin. But to others, the pattern's precision suggested something deeper, a kind of order that refused to fade. Natural rotation, influenced by solar wind and dust jets, tends to drift over time. This one didn't. The phase remained locked, as if stabilized by some inner mechanism or balanced geometry. ESA's Cassis instrument had caught a similar pattern months earlier, during the Mars encounter. Now, months later, the rhythm was unchanged. That constancy hinted at structural integrity, something dense, perhaps monolithic beneath the layers of ice. It was as though the comet's outer dust mask had eroded away, leaving a smooth core behind. Infrared readings supported that idea. The nucleus now reflected heat evenly, like metal under frost. The nickname the Mirror began circulating among astronomers, unofficial, poetic, but fitting. Its surface behaved more like polished alloy than dust or rock, scattering sunlight in a peculiar polarized way that made it gleam faintly, even against the dark. The same negative polarization persisted, the same signature that had once raised eyebrows, but now it was no longer anomaly, it was identity. Every telescope that could track it did. From Mauna Kea's crisp air to the frozen clarity of Chile's Atacama, from ESA's ground stations to the JWST's infrared eye, the object's faint shimmer continued to yield subtle surprises. Even amateur astronomers began capturing its trail, stacking long exposures over nights of patience. To them it appeared like a slow heartbeat in the heavens, a thin white dash that reappeared in precisely the same rhythm, as if keeping time with the universe itself. Those images soon revealed something else. A faint halo surrounded the object, Not spherical, but elliptical, like a soft glow tilted slightly off axis. That shape could mean many things: dust scattering asymmetrically, plasma interaction with solar wind, or even charged particles forming a wake. But to the eye, it looked almost architectural, a shape that seemed made rather than born. Scientists resisted the metaphor. Nature loves symmetry too. But still, whispers returned. If an advanced civilization ever wanted to send a durable probe across light years, this is exactly what it would look like after millions of years, eroded, silent, wrapped in cometary ice, its systems dormant, its purpose long forgotten, surviving only as orbit and form. Avi Loeb called it cosmic archaeology. He wrote that even if it were natural, its presence offered insight into how matter migrates between stars, and how our own future probes might one day be mistaken for comets in other skies. His essay ended with a gentle reminder: when we look outward, we're also seeing our own eventual reflection. That thought resonated with many scientists and dreamers alike. Meanwhile, NASA's orbital models confirmed that Three-Way Atlas's new path was stable for at least the next 1,000 years. It would remain between Mars and Jupiter, tracing a smooth loop every 8 decades. It wouldn't collide, wouldn't fall inward, wouldn't escape. It would simply drift, a foreign moon without a planet, a solitary relic in a quiet lane of the solar system. And yet there was one final peculiarity. Data from December and early January hinted at a slight modulation in its rotation rate. Not random fluctuation, but a slow pulse, like breath. Every few days the 16-minute period shortened by seconds, then lengthened again. A rhythmic flexing that no one could quite explain. Could sublimation still be acting beneath the crust? Could internal stress or resonance with solar tides cause the pattern? Maybe. But the motion was too consistent, too regular to be chaotic. Something about it felt deliberate, not in intent but in harmony, as if the object had found a rhythm with its environment. There's an idea in physics known as tidal locking, when a body's rotation becomes synchronized with the orbit of its partner, always showing the same face, like our moon to Earth. 3i, us Atlas, seemed to be doing something similar, but with sunlight itself, aligning and realigning as if trying to find balance within radiation pressure. No one had seen such behavior before. No known comet, asteroid or fragment had ever exhibited it. It was a new kind of dance, a quiet negotiation between starlight and stone. Somewhere in that stillness, humanity's collective attention softened. The frenzy of early discovery gave way to contemplation. The story was no longer about proof or explanation, but presence. The fact that a traveller from another star now circled our own was enough. It didn't need to be artificial to feel sacred. Public interest lingered, not in headlines, but in hearts. Children pointed to the night sky. Teachers explained how interstellar objects connect galaxies like threads of cosmic pollen. Musicians named songs after it. Writers described it as the first guest to stay. And quietly, scientists kept watching, collecting data not out of urgency but devotion, like monks tending a flame. Even Mars, our other observer, carried the legacy. Perseverance's sky cam, still scanning the horizon, each Sol occasionally turned its lens toward the right ascension where the visitor now moved. It couldn't see it anymore, not with the thin Martian sky and its limited sensitivity. But perhaps it didn't need to. It had already witnessed the first encounter, the first time two worlds together watched something enter their shared sky and stay. As winter ended, the object's glow faded into the background stars, its rhythm continuing unseen. Somewhere between Mars and Jupiter it drifted, a spark from another sun, a remnant of another dawn, keeping silent company with our own. And though it would remain invisible for most of our lives, its story would not fade, because for once the universe had done something it almost never does. It had brought a fragment of its infinite elsewhere home. By February, 3 Atlas had faded beyond the reach of most amateur telescopes. Its coma had dispersed, its light curve flattened into a steady glimmer, barely distinguishable from the faintest asteroids. Yet professional observatories continued to track it with patient devotion. Even invisible to our eyes, it remained a pulse within our models, a whisper inside our math. The orbital data showed exquisite precision. Each measurement confirmed the same slow loop, an elliptical path threading softly between Mars and Jupiter's domains, stable, serene, unlikely. For an interstellar object, it was a kind of miracle. In a galaxy of endless drift, this was the celestial equivalent of a deep breath taken after a long journey. A pause. At NASA's Jet Propulsion Laboratory, a small interdisciplinary team began quietly studying the idea of a future mission. They called it Aurora. The goal was simple: to send a small probe to match orbit with 3i Atlas and observe it directly. No drilling, no landing, just a long, unhurried companion flight, like two leaves drifting side by side in a cosmic current. It would take years of planning, decades to arrive. But the idea itself was already enough to stir wonder, humanity reaching out to something that had come so far to reach us. Still, there were disagreements. Some scientists warned against anthropomorphizing the object, against treating it as a story rather than a study. Others argued the opposite, that wonder is not the enemy of science but its beginning. After all, every great discovery in human history began with someone looking up and whispering, "What if?" And perhaps that whisper was what 3i Atlas had come to rekindle. Meanwhile, subtle oddities continued. Spectroscopic readings detected faint emissions, barely above noise but recurring. A tiny spike near the hydrogen line repeating every few weeks. It might have been nothing. Background interference, solar radiation, cosmic dust reflecting radio frequencies. But its periodic nature intrigued analysts. The intervals weren't perfect, but they echoed the object's rotation in harmonic multiples, as if some resonant process deep within its structure was interacting with sunlight. Natural resonance or faint radio scattering. No one could say for certain. The signal was too weak to decode, too ambiguous to classify, but it added another layer to the already intricate mystery. Philosophers began writing again. Some called 3i Atlas a cosmic stranger that remembered us. Others described it as the universe's way of holding a mirror to our own curiosity. It didn't matter whether it was a machine or a rock. Its meaning lay in how it made us feel, how it reminded us that even in the vastness, connection can appear without warning. For the general public, interest took on a quieter, more poetic tone. People began marking February 7th, the date of its confirmed capture, as Interstellar Day. Schools held small stargazing nights. Planetariums projected animations showing the object's long arc, weaving through our solar system like a visiting thread in a tapestry. In these gatherings, children whispered questions that adults could not quite answer. If it came from another star, what stories does it carry? Could there be others still travelling, still on their way? In a sense, they were right to wonder. Astronomers now suspect that thousands of such interstellar fragments pass through the solar system each century, too faint, too fast for us to notice. Our instruments caught 3 only because luck and timing aligned. Statistically, others are out there right now, unseen, ghosting through the darkness, each a shard of another system, carrying the chemistry of alien worlds. If even 1 in 1,000 remains bound as 3i Atlas did, our solar system may already be home to many quiet visitors. There is comfort in that idea. It suggests that the distances between stars, though vast, are not empty. That material, and maybe memory, flows between suns the way wind carries seeds between valleys. It is called panspermia, the notion that life's ingredients migrate across space, seeding planets at random. Perhaps we are the children of such a journey, the living legacy of some forgotten sky. 3i Atlas reminded humanity that we too are interstellar material. Every atom in our bodies was forged in the heart of an ancient star. We're made of what wanders, and when something from another system drifts into ours, it is less a visitor than a returning relative, older, quieter, reminding us of home. Back in Chile, the Very Large Telescope detected one final trace of its nickel emission before the object dimmed below the detection threshold. Faint, but still distinct. Nickel without iron. Even now, its signature remained unique. It was as though the universe had left us a riddle in spectral code. Simple, unsolved, eternal. And so, observation shifted from data to reflection. Conferences continued, papers circulated, but the tone changed. 3i Atlas was no longer an anomaly to be explained. It had become a meditation on scale and patience. One astronomer wrote, "The object is quiet, but we are not. Perhaps the silence is its lesson. Somewhere between Mars and Jupiter, under starlight billions of years old, the traveller still glides, its motion perfectly ordinary, its meaning perfectly vast. Maybe it's nothing more than frozen gas and ancient dust. Maybe it's something we can't yet imagine. But in either case, its path through our system has already changed us. It has reminded us that discovery doesn't always shout. Sometimes it simply stays. And in that stillness, the cosmos speaks not through answers, but through presence. We just have to listen." By spring, 3i Atlas had faded entirely from visible range. The last optical image, a whisper of grey against the black, was taken by the Subaru telescope on Mauna Kea. After that, only radar echoes and faint spectroscopic hints marked its existence. And yet, in a sense, it had never been more present. Its story now lived inside us, woven into lectures, documentaries, quiet conversations, and dreams. What lingered was not proof, but perspective. The realization that something forged beyond our sun's birth had crossed the interstellar gulf, threaded past Mars, felt the sun's heat, and then, without leaving, had become part of our solar family. The odds were impossible, the timing exquisite, the message silent. Still, it spoke. Scientists continued to refine the models. Its new orbit had settled into resonance with Jupiter's Trojans, moving almost in step with a giant planet, though far behind in distance. Such harmony was rare but stable, like a note perfectly tuned to the solar system's long music. Every few months, gravitational pulls would nudge it gently, keeping it in rhythm. In the language of orbital mechanics, this was called coherence. In the language of poetry, it was belonging. There's an unspoken humility in astronomy. For all our instruments and data, we are still creatures of curiosity, peering into vastness with hope. 3i Atlas reminded us of that. It didn't answer our questions, it deepened them. It reminded us that science and wonder are not rivals. They are reflections of the same desire to know what else might be out there and what that means for us. In those months of observation, humanity rediscovered patience. The waiting between transmissions, the long silences between data releases, the suspended breath of uncertainty, each became part of the experience. For a world accustomed to instant clarity, 3i Atlas asked us to dwell in mystery again, to admit that not knowing can be its own form of beauty. When the final paper of the season was published, its title carried no conclusion: Spectroscopic and Dynamical Observations of Interstellar Object 3i Atlas, Preliminary Findings. Even the word preliminary felt eternal, as if science itself understood that some answers arrive only with time, and that perhaps time is the experiment. A few researchers suggested that we might eventually lose it after all. Solar perturbations could nudge it outward. Gravitational tides could loosen its bond. Someday it might leave us quietly, slipping back into the dark sea between stars. If that happens, it will take with it traces of our system, dust from Mars, photons from Earth, the faint electromagnetic echo of our curiosity. It will carry our light into the long night, unmarked, unsent, but no less real. Maybe that is how the universe keeps its conversation going, not through deliberate messages or machines, but through wanderers that drift between worlds, carrying fragments of one into the realm of another. Each collision, each capture, each moment of gravity's grace becomes a syllable in a story older than life itself. We call 3i Atlas it, but sometimes, late at night, you might think of it differently, not as an object, but as a mirror. Because in following its path we found reflections of ourselves, our longing to belong, our fear of silence, our endless search for meaning in the quiet mechanics of the sky. It reminded us that to exist is to travel, that every atom of us has journeyed before, and that stillness, too, is motion measured across deep time. Perhaps, 1,000 years from now, another civilization will see this same object in their night sky, faint, patient, mysterious, and wonder about the star from which it came. Perhaps they'll point telescopes, write papers, feel awe, and in that moment our own world will live again, folded into their questions, shared across light years through the simple language of curiosity. So we leave 3i Atlas where it now drifts, between Mars and Jupiter, haloed in quiet dust, no longer visitor, not quite citizen, a relic of another sun gently orbiting ours. Its mysteries remain, but they no longer demand urgency, they invite peace. Because sometimes the greatest discoveries are not meant to startle us awake, they are meant to help us sleep, comforted by the knowledge that the universe is still making connections, still weaving threads across the dark. And so we close our eyes, not to end the story, but to join it, to become, if only for a moment, part of that long, quiet orbit of wonder. Let your mind drift now, away from numbers and theories, into the quiet where light travels unhurried. Somewhere out there, 3i Atlas still glides through the dark, a small spark against endless silence. It doesn't ask to be solved. It simply continues, patient and whole, circling a sun that once seemed alone. Imagine its slow motion, the way starlight brushes its frozen surface, the way time itself seems to pause around it. Each rotation takes minutes, each orbit decades, each journey a gentle reminder that everything moves, yet nothing is lost. Our telescopes may no longer see it, but its path is written in gravity, its reflection woven into our night skies. Breathe softly. Think of how every atom in your body once drifted through space like that. Dust from ancient stars, carried by winds older than Earth. We're all travellers of the same kind, bound by the same quiet physics of belonging. The same light that touches 3 Atlas touches you now, across billions of kilometres, arriving as warmth, as calm. Let that thought settle. Let it fill the room with stillness. The universe, vast as it is, knows how to hold you, just as it holds that distant wanderer in its slow, infinite orbit. There is no hurry. There is only motion, and the peace that comes from knowing you are part of it. So close your eyes. Picture the starlight fading gently behind the horizon, the soft hum of space between breaths. And as you rest, remember, every silence in the cosmos is simply waiting to become music again.